Aloha and welcome to the inaugural session of Shadow the Scientist here at the International Gemini Observatory. My name is Jamika and I'm so excited to be here with you this evening. The Shadow the Scientist initiative is housed under the Creating Equity in STEAM or CREST umbrella of initiatives offered by a team at the University of California, Santa Cruz. CREST is an umbrella of programs and initiatives that seeks to create equity and promote diversity in STEAM fields by making the effort to engage students from historically excluded backgrounds and critical thinking in the context of research. CREST focuses on encouraging participation in research practices in order to make students feel recognized as scientists. Students are also strongly encouraged to pay it forward by mentoring younger students, thereby enhancing community access to STEAM research. The International Gemini Observatory is one of 5 programs of NSF's NORLab, which is the preeminent U.S. National Center for Ground-Based Nighttime Optical and Infrared Astronomy. Gemini Observatory is composed of twin telescopes. Gemini North, located on Mauna Kea at an altitude of 13,382 feet, or a little over 4,000 meters, and Gemini South, located on north central Chile's Cerro Pachón. Gemini telescopes observe invisible and infrared light. Gemini's 8-meter or 26.5 feet reflectors collect this light with mirrors that are coated with a special layer of protected silver rather than aluminum, which is the more traditional coating for large telescopes. The mirror is made of ultra-low expansion glass and is about 20 centimeters or 8 inches thick. Gemini has large vents, which are opened during observations, allowing the cold night air to flow through the observatory, which produces more stable images. With a telescope in each hemisphere, the International Gemini Observatory can observe objects throughout the entire night sky. I'm joined this evening by Zachary Hartman, who will be our guide on this cosmic journey as we shadow our scientists who are doing evening observations in the Hilo Base Facility Control Room. The observing team for this session includes Brian Lameau, Charlie Figura, and Pablo Martin Rivello.
A lovely 90-ish% humidity. For Gemini, we have a humidity limit where once the humidity reaches above 85, we have to close the telescope for the safety of the instruments and the telescope itself. So we've reached that limit and we're kind of just in a holding pattern now until the humidity decreases enough and for a long enough time where it would be safe to open the dome.
That's right. So you said for a long enough time, Zach. So there is a specific time frame that we have to wait before we can actually open, even once the humidity goes down.
Yes. So for Gemini, it's 40 minutes below 75% humidity. So we are currently at about 90. So it needs to drop 15, or in order to at least get that point, and it needs to stay below that for a while before we even think about opening up again.
So what we're seeing here right now this is a live view of the summit area and a little bit further down as well. And we can see in the top right corner, that looks like one of the twin Keck telescopes, right?
Mm-hmm.
The white dome, and then to the right of that is the NASA Infrared Telescope Facility as well. And in fact, Raja, we were at Keck a few weeks ago when you were here. We were doing a shadow session there. It was my first one, and Brian was there too, along with Stefan, who is in the audience as well. And it was so much fun. And so while we're waiting to open the dome, y'all are really getting a true taste of what it's like to work in an observatory. That's right, because this happens regularly.
Yeah, I mean, I've observed, so my year here, I've observed, I think I calculated about 35 nights, and I would say about 10 of those have been weathered out due to various conditions. So it's definitely the ups and downs of being an astronomer. You certainly live at the behest of the weather sometimes. So
One of the great things I think about the flexibility that Gemini has is the way in which we can do observing. There's classical or traditional observing, and then there is Q observing. Oh yes, so in the chat, yes, we welcome you to do that. Stefan, would you like to unmute yourself and introduce yourself?
Oh yeah, hi, my name is Stefan Kimura. Like I said in the chat, I'm a graduate of Willamette University. I was part of the Shadow of the Scientists a couple nights, I guess a week ago, when I was running the telescope for the Lick Observatory. And I also met Raja, Jamika, and Brian at the Keck maybe 2 or 3 weeks ago as well. I'm a member of Raja's Salvation Team, which I am one day going to remember the acronym for. But
I'll type it into the chat. How
yes,
about that?
please do. If not, I'll pull it up. But yeah, I'm here just observing this time and hoping to meet some of the people from the Gemini Observatory. And yes, it is very humid in Kona today. It is. I've been sweating all day. It's gross.
Oh, that's right, Stefan. That's right. You're in Kona, so a little bit warmer over there than it is on the Hilo side. That's so true. Welcome, Stefan. So glad that you're here with us as well.
Yes, thank you guys. Good to see you guys.
Definitely. Stefan, I'm also going to make you co-host in case you want to share anything or anything. Thank you, Raja. And so Raja has given us this acronym here for salvation that Stefan was referring to, the spectroscopic analysis of luminous variables and transients in our neighborhood. And so that's the group you were working with, Stefan?
Yes, correct. I was put into contact with Raja through the Ohana Kilohoka group, and I've been working with them for about a year now. And for the last few months or so, I've been helping them run the observations on the telescope.
Oh, fantastic. Well, I certainly, in our session that I joined with you all, you had so much to share, and I certainly appreciated your insights and glad you are with us right now. Okay, and let me just look here. Yes, Tom says very humid here on the south side of the island, but we got some rain that we really needed badly. You're not wrong, Tom. You're not wrong. So, Zach, can we pull up the Mauna Kea Weather Center and maybe have a graphical look at what's going on? And this is a publicly available. I'll drop that link into the chat here shortly. Yes, and then you can actually see when you see a screen that's weather on the mountain and it's a lot of blue and red. That's scary. That is scary. Zach, what are we looking at? What are we looking at here? Fog, precipitation, clouds. How do I read this graph?
yeah, so there are a couple different things on this plot. As you mentioned, the top line is fog and precipitation chances. So just basically, is there going to be rain, or is it going to be, how foggy is it going to be? And then the line below that is the cloud cover. So CC is what it's commonly referred as. And that's pretty self-explanatory. How much cloud cover is there on top in the sky above. Temperature, PW is the pressure. Seeing is a term used by astronomers to describe how clearish the night is. How much atmosphere is how much the atmosphere is going to be affecting your observations as you're looking at the stars. Because if we were up in space, like with the new JWST telescope or any of the other satellite or telescopes we sent up there, Hubble is another one, you don't need to really deal with this seeing parameter. it's really just a measure of how much the atmosphere is affecting the light as it comes to us. So, and as you can see tonight, it's decent, for Mauna Kea, about 0.5, 0.7. That's about average, I believe.
It's about average. Okay.
And for the next couple of days, it is not average. It is below average in terms of how good we want it to be. So the forecast is not looking good for the next couple of nights.
But we are hopeful. And in fact, last night, I believe we had, actually we can see, I know it's already on Friday, but yesterday's forecast had a similar amount of blue and red, but I believe the observing team was able to open for a while.
Yeah, they opened about half the night. And, I've had experiences where, the forecast says, it's going to be crystal clear, and suddenly, it's raining, and it's just like, okay. And then you've had other nights where the forecast says, oh, it's going to be absolutely terrible. And then we have some of the best nights in history. So,
Because Zach, you two already talked about the Q observing. We were kind of muted for a little bit, so I wasn't sure if you talked about Q observing and like how that might interact with the weather. Because like, for example, this were my Keck night. So if I were observing on Keck tonight as an investigator, I would be very, very sad because I would have worked really, really hard for 6 months, a year, getting ready for these observations. If I can tell, telescope time is very, very precious. And then the weather comes in and we're not allowed to observe that night, and we have to repropose for time and everything like that. Have you contextualized like how Gemini is different from that?
Absolutely. We were, thank you so much, Brian. We were just about to get to that since we were talking about the weather, and then yes, to pivot to the flexibility that we have with Gemini, with the Q observing. Zach, what is the difference between classical observing and Q observing?
Yeah, so as Brian was getting at, classical observing, it's you're as a principal investigator, as the person doing the observations, you go to a telescope and you get a night, and you can observe whatever you desire in that night. Principally, you have a program that you propose for, but can see it. But it's also, if you want to pivot to something else, you can do that as well. Versus with Q observing, what happens at Gemini is you apply for time. Anybody in the world can apply for time at Gemini, and you are given a ranking. And then based on that ranking, your program is scheduled, and you have and over the course of a semester, the observatory will try to observe your program. So it's not just limited to one night. This is the night you have to get your observations done. It can be over the course of an entire half a year that your observation could possibly be observed. So both of them have their strengths and weaknesses. And here at Gemini, we use the Q system, while other observatories like Keck use the classical system. So.
Right. And so now you talked about semesters. How does semesters work into the proposal scheme? I mean, we can actually talk about what a proposal is really briefly, and then I'll drop a link to a bit about the Q observing and our semester programs in the chat while you do that.
Yeah, so a proposal is basically you have an idea. Like for my research, I look at nearby stars, and I look to see whether there are these stars have buddies around them, so that they're binary stars. And the way I do that is using high angular resolution imaging, which is through the use of either techniques called Speckle imaging or adaptive optics. And so with a proposal, I would put in, I ask for X amount of hours to go look at some targets to see if they have if they have another star around them. And I write up, the scientific reason for it. I write up why I need to use this telescope. And then you're gonna need to leave.
Yep. Sorry about that.
And then so you write the proposal, it goes into what we call a TAC, which is a telescope allocation committee. And this committee is made up of scientists, astronomers from around the world. And they look at everybody's proposal who has submitted one and judges it based on the technical and scientific merits of your proposals. And then at the end of the day, there's a ranking, and some proposals get time accepted and others not. And then and then at the end of the day, Gemini gets this this information about who's been accepted and who's not, and takes the accepted programs and gives them a band, which in this case is mainly bands 1, 2, and 3, which I don't know whether you have shared.
I'm
that,
not, I have not, because I can't,
Okay.
I haven't joined on this computer
Okay.
yet. So I'll do that once we, yeah, continue.
Okay.
I'm not gonna
Um,
join with audio
So
this time.
Zach, I can bring up our Q planning tool for another night. So maybe an older semester, I'll bring that up on the shared screen that we have.
Yeah,
And we can share with the audience,
And
and
on
then yeah, we can look at that.
yeah. See if you can find one, because I was trying last night and it did not want to. It was empty. So,
Oh,
well,
Oh, yeah,
as you're doing that, I'll explain what the bands are.
yeah, please.
So the bands are basically, there's band 1, 2, and 3. Band 1 is, your project is really important. There's a lot of scientific merit. And so we will do everything in our power to observe your target. And normally that means, 80% of the time you apply for is going to be used observing your targets. Band 2 is you have a slightly lower scientific rating than band 1, but you're still really important. So we're going to try to observe your targets. And then band 3 is really, you have scientific merit, but not as important as band 1 or 2. And band 3 is mainly used as kind of poor weather programs and filler between, band 1 and band 2 observations. So those are the main bands.
yes. Thank you
Yeah.
so much. No, this is so good because, well, for this evening with humidity, would we call that poor weather observing if we could open and the humidity is down for the amount of time that we talked about?
So it actually depends, if we open up, if the humidity drops low enough and stays low enough, and we open up and we look out and the seeing is really, really good. Looking at the cloud cameras that I was showing earlier, it looks a little bit cloudy, but not a lot. So I would actually classify this as usable science weather if the seeing is good and the humidity drops. But that's the question. We don't know what the seeing is like until we get on sky and we take some measurements, because right now everything's shut down and stuff like that, and we can't really get in, or we can't really get an accurate measure of what's going on. Poor weather is definitely when there's bad seeing. So the seeing is very high, so higher than 1 or 2 arc seconds, and an arc second is 1/3600th of a degree. And if it's very, very high like that, that's what we would classify as poor weather. Or if it's the opposite, where it's super cloudy, that would also be considered poor weather.
And in addition to those bands, thank you, Zach, so that orients us to what we could potentially be looking at once the humidity goes down, and we'll check in with our observation team here in just a moment. In addition to our band 1 through 4 programs, we also have a few other programs that we can talk about while we're waiting to get things going. We have the fast turnaround, and we also have the director's discretionary time programs, DD
Megan, do you
time.
mind if I jump in for just a sec about the bands? Because I think it's kind of actually really important to talk about in terms of Q observing and the difference between Q and classical. This is an aspect that I really like. So I come from a classical background of applying for a telescope like Keck or Subaru or Lick, where we have a single night and we observe the targets that we decide that we're going to observe way in advance. And we have some backup plans if the weather is bad, but normally we're pretty stubborn and we just try to observe our really, really faint distant galaxies, even if there's a magnitude of extinction. So that means fairly thick clouds up in the sky, and that's not the best use of really powerful telescope time. And so this band 4 set of programs that we have at Gemini are for what we call weather loss programs. So it's basically well, I don't know if we'd actually technically be in band 4 tonight. Maybe band 3-ish.
Like I said, it depends on when we open up.
But with that, we've got a massive cloud mass
Oh, yeah.
just on the north side of the summit.
Yeah, speaking of Craig.
Yeah,
Oh,
I doubt.
wow.
Even Keck is closed right
Wow,
now,
I see that. That's a massive cloud.
Yeah, I doubt we're opening up anytime soon.
Yeah, so
so it's Keck. They could open up in 10 minutes, but they have different rules for opening and closing than we do.
we also saw last night, Charlie, the relative humidity between difference, even though they're so close on the Mana, there's the microclimates on the Mana.
Yep.
Which
Yeah.
I think it was relative humidity 48
Yeah.
at like sunset last night, and we were at 95.
Yeah, it was really
They
crazy.
come up that north face,
Yeah,
can come up that plateau and be
Yeah.
very different than what it is on our eastern ridge. So
yeah.
That's right. And actually, that's a really good segue to talk about where we actually are in relation to the summit, to the observatory, and where our observation team and where Zach and I are. And so as we said in the introduction, the observatory is in fact near the summit region on Mauna Kea. But we actually are able to run the telescope remotely. And so we are actually down in Hilo in what is called the Hilo Base Facility. And if you've been to Hilo, then we are on the just on part of the campus, University of Hawaii Hilo campus, just behind the Iniloa Astronomy Center. And so the control room was at the front of our building, at the very front of the base facility. And so that's where our observation team is right now. And Zach and I are in a building behind that in a remote observing room, yes?
Yeah.
And so what is this room used for when it's not being used for Shadow the Scientist sessions?
Well, during COVID, we had to make a lot of adjustments in order to be able to still observe. And one of the adjustments was we needed to keep people separated for as much as possible. And one of the solutions was this used to be a conference room. And what they did was they turned it into a second observing room. So if you see me glancing to my left, it's because we have this wall of monitors over here. And I have stuff on the monitors. And so basically during COVID, you'd have the observer over in this room, and then in the main control room, which you can see through Brian's screen, that's where the operator would be. And so that way we could keep our operators and our observers safe during the COVID, the height of the COVID pandemic, over the last couple of years. And now that steadily it has dropped down, we've become more and more comfortable having observers and operators back in the same room. So that's why tonight we're over in this room where we have the access to the screens. And then Charlie, Pablo, and Brian are over in the control room running the show while we're kind of shadowing them from over here.
That's right. We are shadowing them from the building behind. Thank you, Zach. And yes, thank you, Brian. Was responding to, I don't want to mispronounce your name, but yes, he said there looks like there's some rain on the way.
And that comment is from Annalisa.
Annalisa, thank you, Raja.
Annalisa, did I pronounce your name correctly? She's from South Africa, right?
Yes, good morning, Prof, and everyone. I am from South Africa, and yes, indeed, I spotted that rain cloud that's heading your way on that satellite image that you've got in the 11 o'clock position. Great to be with you. Thank you so much.
Thank you. We are thrilled that you are with us from South Africa. How amazing to be able to be connected in this way, and great looking out. So, Brian, this rain cloud, if it continues to make its way here, we're already seeing the high humidity. Could that mean that we have to wait even more time, or potentially not open at all for the evening if that rain gets close?
Yeah, absolutely. So we have a variety of different criteria that determine whether or not we can open. And certainly adding rain, thunder, lightning, hail, all these sorts of things are going to increase the amount of time it's going to take us to open. And that time may be so long that we don't open tonight, but we hope for better weather this upcoming weekend. Yeah, so things change on the Mauna very, very quickly, and that can be for good or for bad. And as Zach mentioned earlier, I've been a part of many classical nights where I went into the night thinking I was doomed, that I would have to wait another year to get observations, which is sad on the time scale of a postdoc or a graduate student.
Yeah.
And things have been absolutely gorgeous up there, or they'll start off bad and then they'll turn gorgeous. I've had many more of those kind of experiences than the experience where things were predicted to be wonderful and absolute dejection hits when thunder and lightning. So yeah, things change quickly and we stay here. I mean, this is very valuable time to everybody. The telescopes are highly valued by scientists across the world. And so even if we can open up for 20 minutes in the night, that's worthwhile. So we'll be here all night until the head of science operations calls up and says, okay, you guys.
What's in it? Oh, sorry, you're right. Go back.
All right.
I heard you guys mention about screens that you might have to share. Maybe we could show off some of those, even though we're not in action.
Yeah.
Kind of for people like what we're looking at.
Yes.
I guess these will be the same screens more or less, just like kind of we're looking at here in the observing room.
Good call, Brian. I was actually just thinking that. What do you want to show? Maybe the telescope display?
Yeah. All right.
So.
Oh, yes. All right. So Zach, while our observing team is pausing right now, if we were actually observing right now, this would be one of the screens that we'd be sharing. And this is the telescope status display.
Mm-hmm. Yeah. So on the screen, there's a lot of things that aren't moving that would be moving if we were observing. But this is, the screen that observers use in order to figure out, okay, where are we pointing? Not seen on here is we have a couple displays for where the position of our targets are. And then we also get some measurements out of here. On the upper right here, you see that there is a seeing value up here. And you see these different numbers under there, P1, P2, OI, and AO. Those are the different guiders that we use at Gemini. And what these guiders do is allows us to basically stay on target over the course of an observation, but also they provide us with some valuable information that the telescope uses to correct for some aberrations that go on and to make the images a little bit better. So they correct for astigmatism, which is a problem in the light path where what happens is your target becomes this oval shape in one direction, normally always like XOR in the Y direction. And we get corrections to that applied to the primary mirror as we go through the night. So that's what kind of is shown up in the upper right there. Then you have some other values here that also kind of deals with what the guiding is showing. Down in the lower right, it shows kind of the different guiders and where they are. So red where they are right now is that they're all parked. So you can see the different fields for the different guiders. This screen in the middle here shows the light path of the telescope. So normally what would happen is you'd have light coming down, it bounce off the primary here, go back up to the secondary mirror up here, and then bounce down to where the instruments are all located down here. And as you can see on here, we have a couple different instruments on the telescope right now. We have NIRI, which is our near infrared imager. We have GMOS, which is the Gemini multi-object spectrograph. It is our workhorse instrument here. It is the most applied for instrument by far of any of the instruments here at Gemini. It has a couple of different modes, so you can take just basic imaging with it. You can take long slit spectrograph or spectroscopy with it.
Mhm.
You can do multi-object spectroscopy, and there's an integral field unit as well. And all of these units, or all of these different modes, allow for astronomers to do different aspects of science on targets. There are a couple other instruments as well. You have in the bottom here NIFS, which is our near infrared integral field spectrograph or a spectrometer. Then you have this thing called GCal, which is actually what GCal is it's a calibration light. So you can shine it back into the instruments in order to get calibration images that can then be used to make your science especially usable. So things like arcs, if you're getting spectroscopy, which allow you to determine wavelength calibrations for your targets. And stuff like that. Also in this port, and although it's not shown, is an instrument called allocation, which is my favorite instrument at Gemini because it is the Speckle imaging instrument here. It is actually what we call a visitor instrument, meaning that it is not technically a Gemini instrument. It is a instrument that has been constructed and operated by a team outside of Gemini. So in this case, it's the NASA Speckle team. And so once or twice a semester, they'll come by and observe targets for the community and their own program for about a week or so. And then the final instrument that's on the telescope right now, and it's not really, it's more of a, it's not itself an instrument. It's a it's an instrument to make other instruments better, or to make the science of other instruments better. And that is Altair, which is our AO system, our adaptive optics system. So what happens is, although we are correcting for some effects of the atmosphere with our guiders, and when we tune at the beginning of the night, we kind of correct out some of those other aspects as well. What happens with the adaptive optics system is we feed the light that comes into the telescope through that system, and it corrects even more of the atmospheric effects. And then we feed that light into different instruments. So normally, when we're talking about the near infrared imager, NIRI, there's a lot of AO programs plus NIRI that occur, along with NIFS. That's also a common program. And by basically feeding the light through the AO system, you correct a lot more of the atmosphere and get more pristine images out of it, more pristine data out of it as well. And then the other, so in the lower left over here, we have a couple of different plots. The big plot, which shows—
Can I ask you a quick question? Sorry.
Yeah.
Since you are one of our world's experts on speckle imaging,
I would not
and it's
say
your
that.
favorite instrument, do you mind explaining to people that might not know what a speckle imager is and how it works and what kind of science cases? Because all the different instruments that you talked about, as you mentioned, like GMOS has a bunch of different modes, and there's different science cases that would use those different modes. And like, for example, for my science, I would never use speckle imaging, not only because I don't like USAC and your instruments, but also because it's not— wait, sorry, did that come out?
Rude.
I thought I misheard you.
But yeah, I would never use that for my high redshift science for a variety of different reasons. But for you, it's absolutely crucial to have those kind of observations.
Right. So yeah, so I mean, so allocation has two modes. So one of them is just a wide field imaging mode, which is similar to GMOS, but GMOS is really limited to observations longer than 30 seconds. After that, when you take data with GMOS, you then have to read the data out. And if you're reading it out at a fast clip, there's only so much time, there's only so fast you can go. And allocation offers you the chance to go really a lot faster than what GMOS can. So there's that side of it.
Mm-hmm.
And then there's the speckle imaging side. So speckle imaging is really, really great tool that astronomers have come up with that basically allows us to get to the diffraction limit of the telescope. So The diffraction limit is basically a limit on how close an object can be to each other so that we can resolve an object. So if an object is too close, we at Gemini are going to see it as a single object. Now there's also the seeing, and the atmosphere plays a huge part in this. So normally for a telescope, we are limited by the seeing. So if nominally if the seeing is, you know, an arc second, your images are going to have a full width half max. Your stars are going to be more bloated than say if you were seeing in like 0.5 arc second seeing. So that's normally what happens with observing at a telescope. But if you add in adaptive optics and Speckle, what this allows you to do is it allows you to beat that limit. And these work in two different ways. So adaptive optics works as you're taking the image on the telescope. So when we use Altair, it's correcting the light as it goes through the instrument. Speckle imaging works in a different way. So Speckle imaging works after we take the data. So we go and we take the data, and then afterwards we run a data reduction on it. We run it through a data reduction pipeline. And so the key with Speckle imaging is that we're taking really, really short exposures. So with Speckle imaging, our exposure time is about 60 milliseconds. And we take 1,000 of those in a minute. And we take several sets of 1,000. And then we take all those sets and we put it through a Fourier analysis. So we move it into the Fourier plane. And basically what this allows us to do is reconstruct the image that we would see if it was taken at the diffraction limit of the telescope. And there's a bunch of math that goes into this, and I'm not going.
Yes.
Some people may like math, but I'm not going to go through the math right now on the fly. And there's no whiteboard in here.
You can draw on that.
Zach, I was going to ask if you have an example of a single speckle image that might be nice to show people.
Yeah. Let me pull up.
And while he's doing that, I actually dropped in the chat an interview with Steve Howell, who's he's a NASA scientist, project scientist on the Kepler mission, but also Gemini NORAD scientist as well. And we have a live from NORAD at Hawaii a year or so ago that I did with our team, and I have the link there. And it's a great show if you want to take a look at it and learn more about speckle imaging, specifically with Gemini. And if you have something you can grab, an image you can grab real quick, yeah, awesome. And then we actually have maybe 4 or 5 more examples in the show that I can pull up to from Steve Howell's.
Yeah, all right. I'm going to kick myself off of the sharing, and then I'm going to share my own screen.
Yes.
All right. So yeah, so let's see here. Okay, there we go. So on the left and right here, I have 2 separate images. On the left is what we take at the telescope. And so if I click play here, this is what speckle imaging looks like as you're on the telescope. It's really short exposures. And what's happening is as the light is coming to us, it's getting interfered with by the atmosphere. And so when we see it on the ground, we see it as a bunch of speckles. Now, if you were to say, take a longer exposure, do 5 minutes, it would appear as what you would see at a normal telescope. But when you do it at these short exposure times, you get this speckly pattern. And that's what gives this name. So what we do is we take a bunch of these, and for a bright target, we only take about 5,000 frames of this. And what we do is we then conduct this Fourier analysis, and we basically reconstruct the image. And the key with speckle imaging is that we have all this data that we've taken before that we can then add in. So on the right here, I have the reconstructed image. And what's going to happen is we're starting with only adding in a couple frames. And so you see this peak in the middle of the image that shows where the primary star that you're looking at is. And what speckle imaging is really good for is finding binaries, finding companions to stars that we, from Gemini, normally we would see as just the single blob. But when you use speckle imaging, suddenly there's another star there. And so as you add more frames to this image on the right, you're going to see a binary companion pop out on the right over there. So this is simply,
Oh, wow.
yeah, so this is simply just basically adding more and more frames into the data, into the analysis, and this improves the reconstruction by basically adding more signal to this reconstruction and allowing us to see what this binary companion here. And so that's the power of speckle imaging, really.
And Zach, just to point out, I think the x-axis on the right, x and y-axis on the right are a factor of 2 zoomed in compared to the x and
Yes.
y-axis on the left.
Yep.
Ah.
Yes, thank you for pointing that out. Yeah, so it very much can resolve very, very close companions. So for example, the diffraction limit of Gemini in one particular wavelength band, in the red wavelength band, which is about 832 nanometers, that's the band that Alpaca uses. The diffraction limit there is 0.025 arc seconds. So remember, for an arc second is 1/3600th of a degree. And so this is a really, really small resolving power resolution limit that we can reach with speckle imaging. Versus, on a night like tonight, if the seeing is, an arc second, that's really what we're limited to if we can't get, if we don't use speckle imaging. So that's the power of speckle imaging. That's why I use it, is to really pick out these companions. And as Brian was saying, for high redshift galaxies, it's not great because you're not going to see anything in these short exposures for his faint objects. I mean, I say faint is about 18th magnitude. So and as you go higher and higher in magnitude land, you get fainter and fainter. And I think for Brian's targets, what's the faintest target you've looked at, Brian?
Well, so just astronomers have a lot of weird systems of measurement, magnitude being one of them, maybe one of the most weird. Magnitude is a measure of brightness or intensity over time for a given area, and a weird logarithm of that. And so the human eye can detect things on a nice clear night of like magnitude 5 or 6. And so every increase of 2.5 in magnitude is an increase of 10, or well, a decrease actually, because it's negative, decrease of 10 in brightness. So what Zach says, 18th magnitude. So what is that? So that's like 10 to the 5. So it's like 100,000 times fainter than the human eye can see. Okay, so that's that's faint for you, right, Zach?
That's faint for me.
That's faint for you. Okay, so 100,000 times. But with a 8-meter class telescope like Gemini, if you're not using speckle imaging, you see that in a second. So that comes out. Those are the kind of things that we even use for maybe our. Well, it's still a little bit too faint for our wavefront sensors, but still, a quick image with GMOS is going to pick those things up. The things that I look at are anywhere between 24th and like 29th magnitude.
Ooh, wow.
That's another 10,000.
Looks like 5 mags is 100 or something like that.
5 mags is 100, yeah. So that's we're now a billion times fainter than the human eye can see. And these are the kind of faintest things that are seen in like a kind of medium depth Hubble image. And some of the kind of sources that we're seeing in the recent James Webb images of the cluster, the SMAX cluster, those were galaxies that were around 29th magnitude or so. So the same types of sources, and those are the very first galaxies that are very, very far away, very faint. So you don't want to use speckle imaging for that. So if I put in a proposal for speckle imaging for those things, even to get diffraction limited, observations, I think Zach would laugh me away from the telescope.
I see, Raja, you have a question?
I do. I was wondering if Brian, if one of your distant galaxies had a bright star next to it, I suppose you could use Speckle then.
You have to be within, 5 arc seconds of it.
Exactly. Or imagine you're looking at a, the bright nucleus of a quasar. You could use the nucleus of the, if it's bright enough, you could use that nucleus for. And Zach, if you have a moment to play that Speckle movie again, I don't know how complicated it is to get that up, but just wanted to point out something with the. You mentioned Fourier transform, and I know those are difficult to explain in non-mathematical terms. The other one, sorry, the movie on the left, the Speckle movie itself. Right. So, so one of the things you can see, I mean, so the analogy I think of is if you're standing on the side of a swimming pool and looking at a light bulb at the bottom of the pool and the water's moving around, this is exactly what the water would do to the image of that light bulb, because it's bending light, but it's bending light, different parts of the surface of the water are bending light into your eyes in, along different paths. And since the water is moving around, you'd see the sort of dancing image of that light. It's the only thing bad about that analogy is we are actually at the bottom of the pool. The light is outside the pool because the higher refractive index material is close to us, and the starlight has been traveling through vacuum for the most part. So apart from that reversal, it's the same thing as the dancing image of a light seen through, a body of water. One way you can think of Speckle imaging is if you take the, as the image of the star was dancing around, you'll notice that it was moving from one position to another, but also some happen to be tighter spots than others, right? Sometimes it's more diffuse, sometimes it's tight. And again, this is exactly because the atmosphere is moving around. So you could easily opt to give more weight to the speckles that are tighter, that are more concentrated than the ones that are diffuse. And the main thing you do in Speckle is you take the brightest point of that speckle and you shift that to the center of your image. You do that for all the speckles. So that's one way of preventing the dancing around from blurring your image. You can think of it in those terms when you're thinking about Fourier transform does more than that, but you can think of it in those terms, and that wouldn't be too poor an approximation to how it magically returns, results in this image on the right. There's no magic in Fourier transform, but effectively that's what it's doing. It's giving highest weight to the tightest speckles, the most concentrated ones, lowest weight to the most diffuse speckles, but it's also aligning them from one speckle to the next. It is undoing the fact that the centroid of the light distribution is moving around.
Yeah, that's exactly right. And another method of doing Speckle imaging is, well, it's not really doing Speckle imaging. It's just what's a good word? Maybe
it's a reconstruction method.
Right.
Reconstruction method. Image reconstruction method is.
Yeah, well, what I was going to say was another way of not really doing Speckle imaging, but taking advantage of the fact that we're going really fast is called lucky imaging, where basically you take a whole bunch of images, but instead of doing any image reconstruction really on them, you kind of look for the best images, the ones that have the best seeing in them, and you take those images as your science result. And so you could do that with the data that you collect with Speckle imaging, but the Fourier analysis is and the shift and add method are both, I believe, more powerful than just straight lucky imaging. So yes.
In lucky imaging, you don't just take the best, you take the few best, and then you can still do the shift and add and line them up, right?
Yeah.
Okay, so Speckle imaging is that used? So we hear NASA's using it, we're using it. Is this a technique that's pretty widely used?
For what it's for,
Yeah.
yes, it is. I mean, some people use there's kind of this split in the community between using adaptive optics versus Speckle imaging. A lot of the public telescopes in the United States have Speckle imaging cameras on them. So Gemini has one here, and then there's a twin down in at Gemini South called Zorro. Then there's the precursor to both Allocation and Zorro at the Wind Telescope called Nessie.
Oh,
Even before that, there was an instrument called Dizzy running around to basically to Gemini North, Gemini South, and Wind. So it would just be on a traveling on a plane like every other month to go into the different places. And then SOAR down in Chile as well has a Speckle camera as well. So those are the main, and then there's a couple at Lowell Observatory in Arizona as well. So those are the Speckle cameras in use in the United States right now.
so with the speckle imaging seems to definitely be a pretty amazing technique to apply to images when we can. And in fact, I dropped into the chat several things into the chat. First, I want to go back, Zach, Raja, to I'm going to pull this up. I'd like to bring your attention to the press release. It says the sharpest image, sharpest image ever of the universe's most massive galaxy. So I'm going to share that. And then I have a little video that goes with it. It's our CosmoView videos. And these are our NORAD press releases. And typically we have videos that go with them. And speckle imaging that's actually used in gathering some of this data. So I'm going to share my screen here. Okay, so this is this is from August. And in fact, yes, they were using Zorro, and then it was the speckle capabilities here they speak about that really speckle imaging that actually enabled our ground-based telescopes to overcome much of the blurring effect of the Earth's atmosphere in order to get better images. And you can see how blurry it is initially, and then over here to the side you can see you have clearer images once the speckle was applied.
Do you
Zach.
have yeah, actually, if you want to pull up, I think it's the third plot on that
Right here?
slide. Yeah, that one.
Okay.
So one of the great things in this paper, this was written by a scientist down at Gemini South, Venu Kalari. And so he had a couple more comparisons, but this one is really great for this. So on the right here, you see two images. So they're of the same area. They're of this R831 or R136. And on the right, you see the Hubble image. So this is the image taken by Hubble from, I believe it was, I can't remember the date. But this was an image taken by Hubble, and you can see that, it looks pretty good. You can see stars, and you can see some of them are binary, or maybe not binaries, but they're close together. And then on the left shows the Zorro image of this same cluster, of the same part of the sky. And you can see how much clearer it is with Zorro compared to Hubble. And that's because the diffraction limits for the two telescopes, Gemini versus Hubble, even though the diffraction limits are different in that Gemini has a much lower diffraction limit versus the Hubble telescope, even though it's in space.
Oh, wow.
That's the advantage of having a 8 meter versus Hubble, which is a
Like 2 meters?
Yep, 2.4.
2.4 meters, even though it's in space,
Yes.
away from Earth's atmosphere.
Yep.
And that's because adaptive optics is correcting for the effect of the Earth's atmosphere.
Well, this is speckle imaging. So
Yeah, so you're correcting for the effects of the Earth's atmosphere. Sorry, not AO, but Speckle is also correcting for the effects of the Earth's atmosphere using the techniques you mentioned. Yeah, so then that advantage of being in space is gone when you're using Speckle or AO, and now it's a question of how big the telescope is that determines the diffraction limit.
Ah, okay. Oh, that was a really great comparison to show, to follow up to what you were showing just now, Zach. Raja, I really appreciate that really clear explanation, because I think that's going to help us understand what we're going to see here in our video. I've actually dropped the link to this video in the chat. Let me pause this real quick. I'm gonna share my screen so we can see it. It's about a minute long. And just again, we get to see more speckle imaging, and then maybe we can check back in with our observing team. Zach, okay, so let me make this large, and here we go. So they were saying that maybe the most massive stars we were thinking are not as massive as we thought, because was it the case, Zach and Raja, that before the speckle imaging was applied maybe to that image, some of those stars that we see now separated with the speckle imaging as individual stars before looked kind of really large. And so and so that's changed how we seem to understand about massive stars.
It's still the most massive star, but
Okay.
it did lower it a little
But not as massive as people thought, right? You're saying because it was really a blend of what, 3 stars? Looks like
Yeah.
it's 3.
Oh, wow. Okay, so that's with the Zorro on Gemini South, but that's Alopeke here at Gemini North, and those are essentially the same instrument.
Yep, they're twin instruments. Alopeke is fox in Hawaiian, and then Zorro is fox in Spanish.
Wow, yes, y'all, this is some amazing capabilities we have to actually see the universe more clearly. So adaptive optics, speckle imaging, pretty fantastic. Let's jump back in here to our observing team. Let's take a look. There we are. Let me read. Yes, they are already pinned. Zach, what is happening with the observing team? It looks.
It's still humid. So, Brian, do you want to give any update on what's going on over there?
And I'll drop can you share the weather screen?
Yeah.
Thank you, Zach.
So you guys were, I had the audio down a little bit. You wanted an update on what's happening here at Hilo Base Facility building?
Because we're all moving around and we look really excited.
We're all staring at humidity graphs and discussing whether we were at 88.6% relative humidity or 90% relative humidity. So there's a very, colorful discussion here about which one of these values we should adopt. But just to give people an idea, we have to be at 75% relative humidity or less for greater than 40 minutes before we can open up. So given that the session this evening, we might run for another hour, so we may have a chance to open up at some point during the session, but the cloud cams are not looking too promising, to put it mildly, at the moment. So we have some fog, clouds, precipitation kind of creeping up on the water there.
Yeah, as Keck becomes a fog cloud.
Oh, Keck has disappeared into the fog cloud. So you all are seeing live what is going on. Yes, Marufa. Yes, thank you. Wow, that is amazing. And just like if you have your backyard telescope or doing photography, astrophotography, it is a beautiful view. It certainly is. It is a beautiful view, isn't it, Zach?
I mean, when the clouds come in and eat them.
It is still beautiful. And you know what? One of the things that on the cloud cams, as an aside, you can actually see some amazing, some amazing shooting stars and lots of different things in some of these videos. And I will drop a link to specifically to our cloud cams where you can get older recordings of the evening, just kind of the whole night observing, but sped up into, it's like 2 or 3 minutes long video. Yeah, so really compressed. But there are some great targets, some great things to see there. And in fact, y'all, if you look in the west image to the bottom right, I am pretty sure that is Maui's fishhook right here, Scorpius. You all see that? With Antares here, this very nice red supergiant. Raja or Zach, can we confirm for me?
Don't ask me. I'm a terrible astronomer when it comes to these things.
Yeah, I don't have a background in amateur astronomy, so terrible.
Time of night and as we're transitioning into winter.
Okay, that's what I was thinking, and I'm super positive that this is Maui's fishhook. This is, yeah, because I can see how it's arcing over. So this is exactly one of the things I wanted to point out. One of the great things about the cloud cams is it really does allow you to explore the night sky in a very passive way just by looking. And of course, you can take some nice screenshots and frames of the images and catch some really awesome phenomena sometimes. Okay, so now as we continue though with being closed, as we are making sure to take care of the telescope, we did look earlier at the telescope status display, which we would be looking at if we were open. But if we could continue that a little bit, Zach, just to give our audience a taste of what it'll be like once we hopefully get a chance to open a bit later in this session, the instrument status display. Now, you talked about GMOS, you mentioned NIFS and MIRI. Is there a way for us to just kind of see what that interface would look like? Maybe familiarize our audience with it?
Yeah, so we do have, much like the telescope status display, we also have the instrument status display, which is this desktop. And share.
Yes.
There we go. All right. So yeah, so this is the instrument status display. I have the ISD, as they're known, open for GMOS. So what happens when we're observing is normally the observer and operator will have one of these open, and basically this will tell us what's going on within the instrument as we run an observation. So normally what happens is when we start up an observation, when it ends, the observer will choose another observation and the operator will begin to slew the telescope. And as the telescope is slewing, the observer will normally set up the instrument. And so what would happen is a bunch of the options here on the display would be blinking, and there you would see some movement a little bit as everything changes to the configuration of the observations. So as you can see here, there are a couple different settings. You have the guider here, and because we're not doing anything with it, it's set to not following. If you're going to use IFU spectroscopy, you have the mask, and as you select this observation and you ready it up and the instrument starts moving around, you would see that go in, and then if you were doing a multi-object spectrograph or an IFU, you would see that kind of fit into there. There's some filters here that we can select, and GMOS has a lot of filters. I can't remember the exact number right off the top of my head right now, but it's a lot of them. Then if you're doing spectroscopy right now, this is set to imaging. So you can see that it's set to the mirror. But if it was spectroscopy, then there would be a specific rating that would be subbed in there, and that number would be different. And then the bottom one is the shutter. And so if we were taking an observation, it would change from closed to open. And that's essentially what's going on within GMOS as you're taking an observation. And then on the left there kind of shows some other information for it, what image we're on, how much of the observation is left. and then some other information as well as to the observation itself. So that's kind of what GMOS looks like. And then we also have a couple for the other instruments as well. So
maybe some people have joined other Shadow the Scientist calls. So like if people have joined Raja's salvation call, Raja and Stefan's salvation call, they were, I think, Roger, correct me if I'm wrong, they were using the CAS spectrograph on the Shane telescope.
That's right.
Yeah, so this is also a spectrograph, typically used for radial velocity measurements.
And the MOS stands for the same thing as in DMOS, multi-object spectrograph. Maybe you said that already. Sorry, Brian, if you already said that.
Tonight, if we were open, is to do a lot of that configuration. So we have all sorts of software that allows us to do that configuration. But for each science case, people might want different configurations. So Zach mentioned filters. Filters are optical elements that go in the light path. So just to orient people, so in the telescope status display, if you can remember, we have light when we put the telescope that comes off the primary mirror. So it enters in the telescope, bounces off the primary mirror, goes to the secondary mirror, and then goes to our instrument cage, and that's bounced off. So that light is bounced into our reflected into one of our instruments using something called our science world mirror.
And if they can see if they can show them the quick flicks page, they can take a look at a moonbow.
Oh, nice.
Ni-
Oh, yeah.
we were-
Can't wait for what I'm talking about.
Nice. Zach just pointed that out to me. Look at that moonbow. Top right corner.
That's cool.
wait, I need to be on the screen to do it. Here we go.
There it is.
Right there.
Wow, that's beautiful. So even though we have the clouds, that makes me smile. Zach, does that make you smile?
Yeah.
Yeah. Okay, good. That makes us smile. And going back to the instrument status display, Brian mentioned the.
I mean, here in Hawaii, we even get rainbows at night. Come on now.
I love it. I love it. Yeah. Actually, it's I don't know that I saw moonbows when I was on the mainland. Maybe I just didn't notice, but it really seemed to be more prevalent here. And maybe that's just me. Okay, so while we have this up, we have a question that I'm going to put out to everyone in the control room, and Zach and Raja, Stefan, or anyone else. Oh, and I'd like to we have some more people who've joined us. So if you're just joining us, I'd like to say welcome again to the inaugural session of Shadow the Scientist here at the International Gemini Observatory. Excuse me. My name is Jamika. Y'all, I'm choking, but I'm okay. 1 second. So sorry. My name is Jamika, and this is Zach. Zach has been guiding us through our shadowing of our observation team, our scientists in the control room. And as we said earlier, and as we can see, right now we are dealing with some weather. And the weather has given us some beautiful moonbows and clouds. But you can see the observatories in the summit region of Mauna Kea. Zach and I and the observing team were actually down in Hilo, in our Hilo base facility, doing remote observing. The observation team is in the control room at the front building. Zach and I are in a remote observing room, mirroring their screen so that we can see what they're doing and also interact with them, follow them without being too invasive. Now we have a question here from Marufa. Marufa says, a few days ago, I Googled live sky card and found an epic photo. 3 comets around the Earth. 3 big comets or asteroids with tails in our solar system. So the question is, would you please explain what this means. I'm trying to see. Live Sky tonight, you'll probably see something. Okay, so Raja, Zach, Stefan, anyone, it's open to anyone. Do we have a response to this? 3 big comets or asteroids with tails near the Earth?
I haven't seen this. I hadn't seen this, but I haven't seen the specific image at all. But it would be cool to look up the link or to Google search this.
Okay, yes, Marifa, if you could, if you have that link, we can check that out. And if not, no worries, can try to look for that a little bit later while something else is going on, and we can maybe come back to that question if that works, Marifa. And yes, and for everyone, your comments, questions, thoughts are very welcome in the chat, and we appreciate everyone's engagement. Raja, please continue. I'm sorry.
No, sorry. I was just going to jump in and make a couple of remarks. One is, nowadays cameras have become so sensitive that the images you're seeing on your screen, not the satellite image in the upper left, but the other 5 images are actually nighttime images, and there's enough moonlight that they look like daytime images. The cameras are just so sensitive. That's aren't these nighttime images that we're looking at?
Yes, these are nighttime images, but absolutely, Roger, you're so right. It does look like daytime. Zach, it is so bright. It is so bright.
And it is close to a full moon. I realize that, but still, people. I don't want people to think these are earlier images they are concurrent images right now taken on Mauna Kea. The cameras are so sensitive and the moon is so bright that it looks like daytime images. That's one thing I wanted to say. Second thing I wanted to say is I'm just so happy to see so many people that I'm recognizing here on the Zoom call. We talked to Annalisa earlier, and she's connected from South Africa. She found out about Shadow the Scientist from the Astronomical Society of Botswana, who is actually, that connection is actually a connection from the island of Molokai. Vicky Newbury connected us to the Astronomical Society of Botswana folks, and I think Annalisa found out through them. I wanted to give a shout out to Arya Tonis, who's connected from Oahu. Arya, you get the award for the most frequent participant in Shadow the Scientist. You've taken part so many times. I really want you to take part in our research program at Santa Cruz this summer. I see 2 of my students, my high school students who worked in the SIP program, Flora and Yael. As Yael had to leave, I don't see her on the call anymore, but they're 2 high school students who have been doing research with our group. I recognize Peggy here. Peggy's a plant biologist from UC Berkeley. It's just wonderful to see. I mean, Hawaii, California, South Africa, and of course, there are many other places that I'm missing here, but it's just so wonderful to see this. And this is really a testament to the amount of preparation you guys have put in, Jamaica, Brian, Zach. So really, congratulations. Oh, Yael is still here. Sorry, Yael. I didn't see you in the, I didn't mean to say you, I didn't see you in the list of participants, but now I see you. Sorry. Thanks.
Thank you. Thank you, Raja, for acknowledging all of those wonderful participants who were here, your students, and others. I wanted to say, I think you mentioned an acronym. You said SIP. Could you explain what SIP is? Because I don't think I covered that in the beginning. We talked about CREST and Shadow the Scientist, but I didn't mention SIP.
No, absolutely. If what you're experiencing today, Shadow the Scientist, if you think of this as, if you're a young person and you haven't met a scientist before, and let's say this is their first time meeting a real life scientist while they're doing science, you can think of this Shadow the Scientist program as something that allows young people to dip their toes in the water of science and see who else is already in that water, come into contact with scientists and the scientific process. If that's what Shadow the Scientist is, SIP is the acronym we have for a program that is been running for 14 years. It's called the Science Internship Program. By the same analogy, instead of dipping your toe in the water, SIP is like plunging into the open ocean, doing a deep dive. It is open-ended research, still being done by high school students, by groups of high school students, and that's exactly what Yael and Flora have been part of this past summer. They've been doing research on different topics, different topic between Flora and Yael, but this is what SIP is. Stands for the Science Internship Program. It's an 8-week summer program in which small groups of high school students, 3 is the minimum group size. Sometimes it's slightly bigger, the group size. Each group of high school students works closely with a researcher, typically a PhD student, and helps them with their research over the course of those 8 weeks.
This is it's a fantastic program, and I did drop a link to it in the chat. Please check it out. I know if I were a high school student, it'd certainly be something that I would want to participate in. It's a great opportunity to learn and to network and to really dip your feet into the science field, into astronomy, and see what that's like. It's pretty amazing. Now, how many participants can you have at a time during the summer, Raja?
So I just put a simpler link. There's a link through the CREST website, but there's a direct link as well. Well, this past summer we had 326 students, high school students from many parts of the world. We had over, I think, nearly 70 international students, 30 or so students from outside the state of California, and the remaining 200 students were from different parts of California. So 326 was the number this past summer. The year before that, it was slightly lower. But, when the program started the first year, there were only 3 students in the program. So it's grown a lot. It's grown by a factor of 100 in the 14 years of its existence, 14 years of the program's existence.
That's amazing. Thanks. It speaks volumes to not only the interest, but to how engaging the program and everyone who participates is. It has to be in order for it to continue to grow so much. Definitely, please, everyone in our chat, please feel free. And we encourage you to please share that link to the science internship program with any young person you think may be interested, and teachers even too, people who do homeschools, anyone who connects with young people and has a love for science. This could be a great way to get them going. All right, so thank you, Raja.
Thank you, Jamika. Thanks for that shout out. I put the application window for 2023 in the chat, and it's for high school students only. This is the only program that has an application. It's a formal program. Shadow the Scientist has a short registration form, whereas this actually has a proper application. It's for high school students only, and they have to be age 14 and over.
Okay. For age 14 and over.
And it'll be in hybrid mode in 2023. It'll allow for remote participation, in-person participation in Santa Cruz, or some combination of the two.
So has it been, was it all virtual this past time, Raja?
This past 3 times because of the pandemic, 2020, 2021, and 2022, it was completely online these 3 years. Well, before that, it was almost entirely in person. There were a few remote participants. And going forward, we'll have a healthy mix of the two.
Thank you so much, Raja. Raja, we're just looking at the humidity, so I'm gonna share. We're looking at y'all look at that middle screen. There is some pretty colors there. Do you see that? Do you see that moonbow? It's still there.
I mean, it's there.
It's there, but it definitely seems like we are not going to be opening anytime soon. Maybe we can jump in and check in with Brian and the observation team to see what they're doing right now with this downtime.
Yeah. So Brian, you want to hop in on that, or? Hi, Brian.
I would be happy to. Yeah. So we're doing the same thing that you guys are doing, actually. But one thing that I thought might be interesting is to look at our sensors. So I know the views are really awesome in the cloud cams that you're sharing right now, and we can see looking down towards Hilo, this giant cloud complex popping over the ridge. But we actually have numerical measurements of what's going on up there, and so maybe that would be nice to show people.
Good suggestion, Brian. Okay, I think we have that up right now.
So I just want to give people the idea that it's not, we don't make assessments based on what we see visually. That in any given night, we have a lot of quantitative measurements that determine what we're going to do. And so, when we're doing Q observing, so we're taking observations for other people, and so we have, certain metrics, certain numbers that will tell us, okay, yes, we can open up, that it's safe to open up. No, we cannot open up. And we use these numbers that are shown on Zach's screen right now to determine that, but also for a particular science case. So in some case, as we mentioned earlier, some people apply for this band 4, these band 4 observations, and that could be bad image quality. So the atmosphere could be blurring, or the ground layer turbulence could be blurring out what we're seeing with the telescope. It could be clouds, so on and so forth. And so those are, poor weather programs where the science is actually made for weather. But if we have, an observation that needs really, really good image quality, that needs, no clouds in the sky, then we have to make assessments of that. And we have quantitative assessments that we make, and we are not allowed to deliver data that are of worse quality than the science team requests, because that might mean that they don't get enough signal in their observations to be able to do the science that they want to do. So one of my daytime jobs is to, and Zach's as well, is to act as a contact scientist for the teams that are proposing for the telescope. So we go through this process as Zach so eloquently put earlier, where the time allocation committee decides, who gets time, who doesn't get time, what band that goes in, and that's great. So we have everything settled for a certain semester, but then we have to get those observations ready. So unlike a classical night, where I'm a principal investigator and I'm, determining what I want to observe and the way I want to observe it, here it's me observing for another principal investigator, and so they're not going to actually be here, because it changes when the weather changes. We switch programs, and so I don't just call up every scientist in the world and say, hey, I'm on your target now, wake up, time to go. We get things ready ahead of time, so that people can sleep, for example, and rest easy that we're taking the observations that they need. But we don't know exactly for every single scientific program. My expertise is in galaxy evolution, distant galaxies. Somebody asked a question about comets and asteroids in the solar system. That's actually a lot of what the observing plan is tonight. So if these clouds and this humidity magically go away, we're going to be observing Titan, so moon of Saturn, Io, moon of Jupiter, a bunch of asteroids. And so I don't know that science super, super well. And so we need to get things, nice and ready way ahead of time. And so Zach and I work with the science team, and during the night we determine, okay, well, is the weather good or bad enough for this observation? And we can't make that determination ourselves in terms of the scientific quality. That's done, in our daytime jobs with the science team, so that we don't have to think about that at nighttime. And so mostly our job at night is then to assess the weather using these various metrics, the graphs that Zach's showing. And then we determine, okay, are we okay to be observing this program, or shall we switch over to a program that takes a little bit worse conditions? And so maybe I'll pass it back to you, Zach, for kind of explaining what we're seeing on the screen.
Yeah, so on the screen here, I'm going to draw your focus first to the lower left two that are labeled weather graphs and wind graphs. So the wind graph is self-explanatory. It kind of shows the wind speeds in different directions and overall. And then this plot above shows a couple of different things. It shows, let's see here, it shows temperature. It also shows the wind speed. but most importantly, it shows the humidity in a couple different places. And the humidity, as you might see, is hovering, about 100% to 90%. So, it's definitely not decreasing as we had hoped. But the other four over here correspond to what we get out of our guiding system, which is what I alluded to earlier. So it shows the corrections to tip tilt and astigmatism. So two of the factors that might cause our image quality to decay. This provides some correction for it. Roger, you had a question?
Oops. So there's a question from Tom
Yes.
about the. Have you guys answered that already? I
No.
didn't.
I don't think we
Okay.
did.
Okay. I think it actually damages the instrument. It's not just it's got nothing to do with seeing.
Yeah, definitely. If we were
In the chat, so yeah, it definitely can damage the instruments. And so, as I mentioned, our SOS is Charlie, Science Operations Specialist. Charlie and Pablo are here to stop overzealous observers like me from taking observations when the conditions aren't right for it. Because yeah, that serious damage to the telescope instruments can happen if humidity spikes. And Charlie, maybe you can speak.
The probably one of the biggest dangers of high humidity is that the dust accumulation that always happens to some degree on the mirror, when there's high humidity, it's much harder to remove. We go through a mirror cleaning process generally once a week. A team goes up there, and our day crew goes up and uses pressurized CO2, carbon dioxide gas, to clean the mirror. And that works fine for the small amounts of dust that normally accumulate as part of regular operation. When you have high humidity, it kind of gets sort of muddy, as it were, and it just sort of bakes on there, and it does not come off easily. So we try to avoid that. That's our first and primary concern, is taking care of the mirror. And obviously instruments don't like that either. Most of the instruments are in dewars, or kept at very cold temperatures, environmentally controlled. So they're a little bit less of a concern than the mirror surfaces.
Thank you so much for that, for those insights, Charlie. I didn't not, although it makes sense though, that the humidity can increase the amount of dust particles that are, adhered to the mirror.
Yeah.
And I actually didn't know that we did the cleaning once a week.
It's generally about once a week if the conditions are right, if the conditions are good. If the humidity is, interestingly enough, if the daytime humidity is high, they'll put it off because you don't want those conditions there either. In fact, if the humidity is high, that CO2 can end up freezing some of that humidity on the mirror, and that's also bad. So we want to avoid anything on our mirror as much as we can. We expect a little bit of dust to accumulate, but dust conditions are another thing we watch out for. And we have sensors that monitor how much dust is in the atmosphere. So if that rises too high as well, which can happen when we have high winds, we'll close for those kind of conditions too.
Oh, yes, and that makes sense, especially with the wind. I know sometimes driving up to the summit, when we have the dust trail behind us, the wind, I have to turn on the windshield wipers because my windshield just gets so dusty. And in fact, sometimes I can't even see. You try to clean it, and all the particles don't actually come off. And I didn't really think about that in relationship to the mirror, but yes, that has to be something huge. And of course, that can scratch the mirror too. I'd imagine having all of those particles. And so
having that stuff on there, if it moves around, and the CO2 cleaning, it's pressurized CO2, so that's going to drive stuff around with some force. So it's the best way to clean the mirror, but you also don't want to have a lot of stuff on there when when you're doing that process. That's why we don't wait too long between individual cleanings. For people who have not been in that kind of environment, it's kind of surprising to be up at the summit because it's so arid, it's so dry. Every footfall, if you step in, off a paved path and onto the cinder surface, every footfall raises little clouds of dust. So a good wind can just easily stir up a lot of dust right from the summit itself.
Oh, yes, you're absolutely right about that, Charlie. And I'm glad you give those details so that people who have not been here can kind of imagine what that's like and immerse themselves in what that could be, what that could be like to experience. And I've even tasted some of that dust just as we're walking around, and I hadn't really thought about it and how that dust affects the observatories, but and the telescopes. But that dust really does get everywhere, and it seems to be really fine dust too, particles. Does the particle size change? And I imagine that does have an effect on the mirror as well.
Yeah, the higher the winds, the bigger particles can be driven. There's a lot of very fine dust. Basically, it's volcanic ash. Volcanic ash is little rock particles. And there is also a lot of glacial weathering that's occurred on the summit. So there is
That's right.
Just not decayed vegetable matter. It's very arid, very lifeless up there, or nearly lifeless up there.
Nearly. Well, thank you for those insights, Charlie. Aria asked a question, Charlie, why do they use the carbon dioxide to clean it? Aria, was that a good answer to your question, or do you need a bit more clarification?
Why don't we clarify that a little bit more?
Yeah.
Okay, yeah, please do.
The CO2 is reasonably inert to the silver surface, so it by itself is not going to damage the surface. Any kind of liquid that's used would, you have the same problem. If you clean your windows at home, you're always going to leave some kinds of streaks unless you polish it really well. And we don't want to have physical surfaces touching the mirror because it's a very, very thin layer of silver, and it is actual silver on that mirror. It's a front silvered mirror, and it does degrade over time. And every few years, 3 to 4 years, by plan, I think, we resilver that mirror. There's a facility on the bottom level of the telescope building. We actually remove the mirror from the telescope, drop it down, carefully lower it down a shaft to the bottom floor of the building. It's 5 floors down, where we have a recoating chamber. They remove the old coating, they put a new one on, and it's actually been quite a bit longer than usual since our last coating due to I believe first volcanic eruption put it on hold, and then we had a series of protests at the summit in 2019. So 2018 there was a very substantial eruption in Puna of Kilauea, and that put a lot of particulate matter into the atmosphere. So they did not want to resurface the mirror at that point. That was 2018. 2019, there was protests that kept us from doing that work at the summit. And then, of course, 2020 and 2021, we were fighting very strongly against COVID. Hawaii, the state, and the observatory has been very proactive and about being exceedingly careful about COVID precautions, much more so than many places I've been. And so they decided to delay because that process, unmounting the mirror, coating it, and remounting it, takes a lot of manpower. So you have to have a lot of people, a lot of person power. You have to have a lot of people up at the summit to do that work and then to recalibrate things once it's reinstalled. And so the conditions now have gotten to the point where they feel that they can safely do that. and get caught up. They actually resurfaced the smaller secondary mirror. It's only 1 meter across. It's much easier to work with. Last year during our summer shutdown in September of last year. But we're doing the big mirror, the primary this time. So it's going to be a big job. But because it is such a big job, touching it with any kind of a physical surface, polishing rags, anything you want to avoid, it'll damage that silver surface. And liquids will tend to leave streaks. So we use a compressed gas, an inert gas that won't damage that silver surface, but will blow off any particulate matter without too much difficulty. Probably far more answer than you were looking for. But when we're surrounded in fog right now, you'll see we are right in the middle of the cloud. We're pegged at 100% humidity. So.
Oh, wow. And Aria says thank you. Aria says thank you, Charlie.
By all means.
And
in 3 days.
Yep.
So actually, this will be the first and last Gemini North Shadow the Scientist before the shutdown. So we're shutting down the telescope in 3 days, and that's not only to recode the primary, which is sorely overdue, but to do a lot of instrument upgrades and do a lot of refurbishment. But so if we're sucked in up there, so if the humidity is really high, do you think we'll start that work immediately?
They might, it depends on what the conditions during the day are. Humidity can rise and fall in different ways through the day. We often will see increases in humidity toward the evening, and then that then may fall off toward midnight, and they can stay low through at least part of the day. I don't know for sure what they'll do here. They may delay a little bit. There is a lot of work to be done. It's not just, as you mentioned, it's not just a mirror. They pull off the whole acquisition and guidance unit. So all of those instruments that Brian and Zach have discussed, they all come off the telescope. All of the acquisition, the other cameras that are not the science cameras, but help us point the telescope in the correct location and help us correct for atmospheric conditions. All of that comes off, and this gives the engineers, the technicians, a chance to do that heavy maintenance that just can't be done with the instruments in place. Some instruments will be warmed up from their cold temperatures. Their doers will be brought to room temperature, so they can be opened up and work can be done on the inside. That's not done otherwise, because it takes days to bring these things up to a temperature that we can work with, and then days again to cool them down so that they're cool enough to take the scientific data that we need. So these are big tasks. So I suspect what will happen if the humidity is too high, they may get started on some of the other tasks with the detectors and just hold off on the mirror until they can. Fortunately, the guidelines for doing work with the mirror and the equipment during the day are a little bit less stringent. The dome has, just like many houses do, and certainly the control room does, some good air conditioners. And those air conditioners will help keep the humidity down. We've got these huge shutters on the dome. We've got these big vent gates to try to equalize temperature inside and out when we're under normal operations. But when it's closed up, these air conditioners are running. So that will keep the humidity inside the dome a little bit less, not as low as we might like, but that might be sufficient for them to take care of things. And if it's good enough to remove the mirror from the telescope, I think that conditions down on the first floor are a little bit easier to climate control, and so they might have better luck doing it. So this may not, high humidity may not slow them down. It's a problem when they're doing the weekly cleanings, because the mirror is sitting right up there at top. And if they can delay a day or two, then they will. And that's not a big deal. And sometimes they'll say, well, not this week, and we'll do it next week. And that's not a big deal. But I suspect that they will probably want to get as quick of a start as they can on the mirror recovery.
That's a great question.
The process will take quite some time, I guess, because
It-
they have to move it carefully,
Right.
slowly, and then that protected layer of silver recoding, that's gonna take.
So it takes about 2 days. I know it takes about 2 days to remove the silver, the existing silver surface.
Wow.
The removing the mirror, I think takes about a day. It's actually a very complicated procedure. That mirror is held in place
Mhm.
through a number of actuators.
Yeah.
And airbags, pneumatic airbags that help support the weight of the telescope and allow things to flex just the right way. And so there is a lot of mirror attachments that need to be removed. It's not just a matter of unbolting a few things and getting the hoist cradle on it. It's a pretty involved process. But I believe that process that they can get it unmounted in about a day. But basically, they have to drop. They have to remove the A and G, the acquisition and guiding unit, the detectors first, and then they actually drop the.
Is there audio going on right now? I can't hear anything.
Oops.
Me,
Yes.
me neither.
Oh. No, that was, can you hear it now?
We can hear it now.
Oh.
Yes.
Sorry, that was me. I forgot I muted something for 20 seconds. Yes, please continue, Brian. Oh, Charlie. Sorry,
Yeah.
Charlie.
They've been under the summit crew. There's a team of generally anywhere from 3 to 5 people who are up there on a daily basis through the week and occasionally on weekends to do normal maintenance, but their schedules have been loaded for at least the past 2 months with some very intensive preparations for the shutdown. But those preparations have actually been going on much longer than that. In fact, I know that for the past year, they've been talking about upgrades to the coating chamber and getting the supplies on hand and replacing parts of the coating chamber that needed to be replaced so that they could do this. In fact, working with the small mirror last year was done, even though the primary needed it more, was in worse shape. They chose to do the secondary first because it's smaller, it's easier to do, and it's been a little while since they used the coating chamber. And so that would help them diagnose any problems that the coating chamber might have, which are easier to deal with the small mirror, but you definitely want to have fixed for the larger one. So they've been working very hard for the past year, but certainly for the past few months. Their schedules have been very full, and they have the process choreographed, is probably the best word for it, because it is a giant. There's a lot of moving parts, literally and figuratively, here that they need to coordinate and make sure happen at the right time. And right now, I think the operators and observers these last 3 nights are just hoping that we can get through these last 3 nights without anything without anything failing. It's kind of a, how long can you tread water?
Uh,
And of course, if we're closed for, high humidity, at least nothing's breaking. So
The state crew are taking some well-deserved vacation right before the shutdown.
they are going to, because they are going to be very busy.
Absolutely. Thank y'all so much for these insights. Charlie, great detail. Let's jump to the chat real quick. And for those, for our observer team in the control room, Zach is now sharing the shutdown video of Gemini South. This is from July of 2012. And we'll let that play in the background. We'll come back to it. And I'd love to hear some insights, Brian or Zach or Charlie, on what we're seeing. But let me get back to the chat real quick. We have a few follow-up questions. So yes, Aria said that those were awesome responses. Also, Tom did too. Thank you so much. Now we have a follow-up question about the humidity. Would you presume that some of the salt content also, because of our location, contributes to the high humidity or to the effects that the humidity negative effects the humidity could have on the mirror and the instruments?
Question is kind of like, is it
Salt
possible?
corrosion
Yeah. So basically anything that gets on the mirror, right? Like, so whether it's, the dirt that condenses together because of humidity, somebody sprays Windex on it because they think it's a good idea. Cleans the protection. But
So that's not what it is.
Right. So yeah, I am not, I'll be honest, I've not heard of any discussion about salt deposit being a problem. I think that typically anything that's evaporate, when you have evaporation, salt deposits are a problem when you have that liquid seawater that is splashing over things. So, down at sea level, salt is a huge issue. But any moisture that's up that high is going to have evaporated. It's going to have left the salt behind. I have not heard of any concerns about salt.
And I think this is generally true of observatories. I haven't either. At lake, which is at a much lower level, smoke particles from nearby wildfires are an issue, but not salt.
Definitely. And as I mentioned earlier, the volcanic eruption in 2018 was a huge concern because, an eruption can spew a lot of that ash, little bits of rock, very, very high in the atmosphere, much higher than Mauna Kea. And so it can, that stuff can rain down for a while. So we had high particulate sensors and we were closed for quite some time the summer of 2018 because there's just too much stuff in the air. But I've never heard of I've never heard of an issue with salt. And it's quite possible the summit crew could tell me otherwise. Our telescope technical manager might say otherwise, but it's not something I've ever heard anyone discuss. And the scientist part of me, who used to teach earth sciences, would not expect to have salt at that altitude.
All right. Who was that? What was that question from? So thank you for your response. And actually,
That was from Annalisa. That was from Annalisa.
That was from Annalisa. Okay, thank you, Roger. Thank you, Annalisa, for the question and everyone for the response. Yes, and of course, I didn't think about that. Certainly at sea level, we have a lot more issues with the salt, but with the wind blowing things so much, I wasn't sure when I saw the question. I thought, oh, that is an interesting take. I did not think about salt being an issue here. So I appreciate all the questions.
Jamaica, about the bog. So
yes.
But yeah, or if you're going to get to it, yeah. But,
yeah, sure was. Please go ahead.
Yeah. So Ari asked about how much bog is a problem on the summit, and so as you mentioned, when there's big eruptions, that can be a problem. But like kind of for the normal royal, Kilauea is still active, but the trade winds generally take the fog away from the summit
Exactly.
and move it to the Kona side where Stefan is.
Right, so the trades are coming in from the, from the east, from the east to northeast, generally. And so stuff from, fog from Kilauea is typically blowing away from us. That could be corrosive to the mirror, but again, I've never, I have been operating here for almost a year and a half now. So I'm actually one of the newer operators, but that's not something I've actually heard of an issue. And Kilauea has certainly been erupting for just a year now. The latest eruption cycle started at the end of September. And it's really neat because we can see that glow from the eruption in those same cloud cameras that are now showing us the inside, what the inside of a cloud looks like. But we can see that glow from Kilauea. But yeah, I don't think we've ever had an issue with. We haven't had an issue with fog since I've been here. And, the two factors here are trade wind directions you mentioned, and the inversion layer. There is what meteorologists call an inversion layer, which is essentially a temperature inversion, where it gets warmer as you go up, and it's actually colder, but the atmosphere is colder at lower levels, and that traps moisture low, and which is why it can be pouring down rain and have a thick overcast here in Hilo, and the summit is as dry and clear and beautiful as can be. Right now, earlier today we had thunderstorms actually, which are very, very rare, and they break the inversion layer. They can dump lots of moisture at those high levels. But normally the inversion layer keeps pollution of all kinds, water vapor, but also, human caused pollution and fog down below lower levels. That layer often sits around 9,000 feet. We're up near 14,000. So we're usually quite safe from that. But we pay very close attention to that inversion layer and how strong it is and at what elevation it is, because that'll tell us a lot about, a lot of what to expect for the night. Right now, the inversion layer is pretty much non-existent. That's why we are pegged on saturation.
That is it. We have I have a question. We'll get back. I think that Vonnie will get back to your question in just a moment. But you did mention about the eruption, how we can see that glow. And I dropped in the chat a link to the 2021 Halema'uma'u eruption caught from our cloud cams. Zach, could we pull that up?
Yeah.
And Arya says, "Thank you for the awesome response."
Really awesome. I think I was on tech this night, and saw this in the Gemini cloud. Yeah.
Nice. Okay. And then we can actually, yes, there we are. Zach is showing it here. It's really amazing how beautiful it is.
I love it.
And Brian, you said you were on Keck that night?
I was observing on Keck, yeah, and I was observing with my wife actually, and so I was paying attention to the observations, and she was watching the cloud cams, and then she said, "I think the volcano just went off." And so just to speak to Arya's question, I mean, we didn't have to close. There was no mention of this. There was, no problems with the observations, but yeah, a really spectacular show that night up in the sky because we got some really wonderful data and on the ground. Right?
And we absolutely that that is beautiful. It is beautiful, but that is something that many other places maybe don't have to think about is volcanic ash.
It's also something that a lot of other places may not have to think about is earthquake, which we have not infrequently. We have some of the most the telescopes up at the summit here are actually some of the most sensitive seismometers in the world, as it turns out, unintentionally so. Our acquisition and guidance equipment can tell when there has been when we have earthquakes. We can see that the shakes show up in the guidance guidance plots. So we have that to deal with as well. And usually that's not a problem. If you have a very strong shake, we might close down until the engineers can check over the systems. Generally the next day they'll go up to the summit, make sure that nothing was damaged, nothing's out of position. But for the most part, most of the earthquakes we have are very small, and so we see them and we go on with life.
But that does make sense that they would be very sensitive to any kind of seismic activity. Wow. You were speaking about mirror coating a little bit earlier, and the video was playing, but I'd like to, if I'm gonna drop this in the chat real quick. This is another view of this is a video of the mirror cleaning at Gemini South. I'm going to drop it in the chat, and then if I can find the chat again, here it is. And then if we could play that. And I would appreciate anyone's comments on what we're seeing as we're watching it. And then we'll come to your question, Vonnie. And thank you again for all the comments and interaction in the chat. Yes, yes, yes. All right, Zach's gonna pull that up and share. And let's take a look at the mirror coating. All comments welcome. Charlie, Brian, David, Zach, Raja.
You can see the lift underneath the mirror cell. They've already removed, there's that white frame there. They've already removed most of the, in fact, all of the detector equipment from that frame. And so that yellow frame goes up to carry and lower the mirror cell. And then they're dragging the mirror cell out. And again, that's 8 meters, so figure 24 feet across diameter. Should have the people up there on the catwalk there, kind of really give you a sense of scale.
It sure does.
So the whole mirror cell does not get lowered down. They actually remove the mirror from the cell. They are right now removing all of those little connections for the pneumatic controls that help support the mirror. And I'll put the mirror cell back for the time being. The floor drops down, but the floor can't handle the load of the mirror cell. So they drop the floor down, and then they drop there's like a very high capacity hoist in the ceiling of the dome. I don't remember what the load capacity is, but that they lower the mirror cell down with that. And then once they get it down, they're going to start doing the coating stripping. They spray it with chemicals that will help remove that, and they'll actually cover the surface with paper towel that will help hold that chemical in place and let it have time to work. It's like I said, it's about a 2-day process normally to remove that coating. And as you can see from the video, they're just continually rotating that mirror to different positions to make sure that it's uniformly clean, that every area is every area is equally is treated equal. So they lifted it up to drop it into there's a different cradle that holds the mirror during the coating process. So they've just set it on that. It's going to go now into the coating chamber, and there you can see it in the coating chamber. There are three arms to the coaters that actually apply that silver, and you can see the surface getting shinier and shinier in steps, but they work outside to inside. And then when that's done, they'll put it on that moving cradle as opposed to the coating cradle. Actually, at this point, they may just lift it up. I don't remember if they do drop it back down before they hoist it up. And they're gonna do some final cleaning to it, post coating cleaning. And then they'll pick it back up and reinstall it. I believe this video will show them reinstalling detectors as well, but I'm not positive. So. I don't know about you, but I think hoisting that mirror is probably the scariest. The scariest thing of this whole process.
That's why they got some practice.
If you look in there, you can actually see all those actuators underneath the mirror before they drop it down.
Yeah.
So there are 110 something actuators underneath there that actually apply pressure to different parts of the mirror to actually change the shape of the mirror. It's that while that's a big glass mirror blank,
Okay.
it is it's flexible, and as the telescope points to different parts of the sky, the shape of the mirror changes. And so we have a very sophisticated mathematical model that will push on those actuators. Those actuators will push on the mirror to try to keep the shape of the mirror exactly what it should be to give us the clearest image possible.
That is some process. It really is amazing to actually see, especially to see the people next to this gigantic mirror. Yes, Tom, the mirror does weigh a little bit. It does weigh a little bit. That's so true. And so this is about to happen at here at Gemini North. And so tomorrow, the shutdown officially begins. And as you all were saying earlier,
Monday.
Monday,
Well,
in 3 days.
okay, if they want to start it 2 days early, I can live with that.
Science users might not be so happy.
They would not be happy.
Sometimes the scientists are not right.
So Monday, this process will start.
You tell them, Charlie. You tell them.
Monday.
So we have a couple more nights on the telescope to try to keep some observations through the clouds here, but actually it's gotten much nicer.
It has. Oh, I see your hand, Raja.
I know we are well beyond our 2 hours, so I hope I won't take too much time. I just want to make a couple of quick points. One is, earlier Arya was asking about carbon dioxide and cleaning it. Dry ice is solid carbon dioxide, of course, and the fact that carbon dioxide goes straight from ice to gas without going through a liquid phase, it sublimates at room temperature and pressure, is of course makes it great for this kind of cleaning. In addition to the fact that it's inert, but the fact that it doesn't go through a liquid phase, which is just bad for everything, telescopes, coatings, instruments. I don't know if that was already said. I just want to point out that dry ice is something that is solid carbon dioxide. That's one thing. Second thing I was going to say is it's just been such a wonderful discussion today, in spite of the dome being closed. It's just a tribute to you guys. What a great group from all over the world. Great discussion. And I wanted to leave people with I'm sure you guys, the astronomers in the call may know the answer to this, but we were talking about comets earlier, and comets have tails. What are those tails? That's my question to the group. What is a comet tail? Is it, what is a comet tail? An animal has a tail that it can wag. If it's a dog, if it's a cat, that's not good news if a cat wags its tail. But what is a comet tail? That's my question to the group.
What is the composition of the tail of a comet?
No, what causes the comet to have a tail?
What caused it? Is it not the solar wind?
It is, absolutely.
Oh.
Solar wind, yes.
Oh,
Yeah.
yeah, Tom says, yes.
Yes, absolutely. There's a misconception out there that when I teach my introductory class, and I see this misconception a lot. People think it's a trail, as in think Hansel and Gretel. Like, Hansel and Gretel went from home into the forest. They left a trail of crumbs behind them. A comet doesn't leave behind materials a comet's tail doesn't tell you where it came from. It tells you the anti-direction of the sun, the anti-direction of the sun, because it's the light of the sun that has not just the power to sublimate the comet, just like we're talking about dry ice and carbon dioxide here. That's a lot of the ices that are on comets. They get sublimated, not liquid, turned into vapor. And then the pressure of sunlight pushes it in the direction away from the sun. So the comet tail always points away from the sun. It doesn't always point in the anti-direction of where the comet is traveling. Anyway, I just wanted to mention that the Astro 101 instructor in me wanted to say that.
Well, as a student, I will say thank you for asking that and for clarifying that, Raja. Thank you so much. I wanted to say mahalo. Oh, he just popped out. Stefan just left and he made a comment here in the chat. But I just want to say thank you, Stefan, for being here. And Raja and Vani, we're going to come back to your question next. Raja, for speaking of comets, we have and debris tails. When we have meteor showers, and of course meteor showers are, the Earth coming into the path of the tail of a comet. That's something that I've had to I've recently was asked to explain a little bit more to, and that is how I knew that was the solar wind. So thank you for that pop quiz.
No, meteor showers are wonderful, right? The comet is blowing this wind out of the sun is blowing this wind out of the comet, and then our orbit around the sun is causing us to have a relative velocity relative to these cometary tail particles, and it's like stuff hitting our windshield when we're driving, on a highway. That's what a meteor shower is.
Yes, and we actually have some good ones coming up soon, but I digress. Thank you, Raja. And actually, Raja, if you could keep your hat on, and everyone, your educator hat on, Vani's question, let me get back to your question up here. Vani, one moment, let me just find it here. Yes.
And sorry, Rob has pointed out exactly that comets can have a trail and a tail. That's exactly right. And those two things are related because the solar wind can cause the outer layers of the comet to fragment, and then they can get left behind. Those two things are not unrelated.
Oh, I didn't realize that.
Yeah, so the directions of those two things are different, right? Because one case it's a trail, one case it's anti-solar direction.
Thank you so much, Rob, for that extra detail. Okay, and so keeping your professor hat on, Raja, Vani's question, let me find it. So what should an interested young budding astrophysicist do to succeed in this profession, Raja? And I know that's a really broad answer,
question.
Sure, yeah. But yes, broad question, but maybe some basics here?
I think the simple thing is work hard. If you're passionate about something, work hard towards it. Self-learning, I'm a big proponent of self-learning. It doesn't matter which institution you're in, whether they offer classes or not. Self-learning is such a powerful way to learn. There's so many resources available now online, and even in old-fashioned libraries. But it depends also on where you are in your academic journey. If you're in high school, the science internship program is one of several wonderful opportunities. If you're in college, there are things called research experience for undergraduates that you can get involved in. And if you're in graduate school, your primary work there is research. So you're doing a lot of that as a postdoc, as you are, Zach, you're doing research. So it really depends on where you are in your academic journey. I think if you're not yet in college, then, the number of opportunities are limited. In high school, again, we have the science internship program. There are other programs like it. But it depends on where you are in your journey.
Vani, thank you, Raja. Vani, I hope that was a good takeaway for you to share out with your students. I'm assuming you're a teacher since you asked that. I kind of know, but yes. I can have a follow-up if you'd like, Vani, but thank you for the question. And thank you everyone for being so engaging. I really do appreciate that. All right.
Can I ask you
please
to share some of your experience with Mauna Kea scholars, since that's Hawaii-based? institution, and that there is some connection between what we're doing here tonight and that organization.
Absolutely. Let me find a link here. I actually just had it up, Mauna Kea Scholars. And so as Roger was talking about earlier, the science internship program is for high school students, and it's to give them some access, some exposure to really see what it is like to be an astronomer and all the different ways to participate in an observatory. And here in Hawaii, we have something similar. It is for high school students as well. I'm going to drop this in the chat. Mauna Kea Scholars, and Zach, if you wouldn't mind, could you share just the main screen there? It happens to have a really great image, a really great view of Gemini in the background. Mauna Kea Scholars, yes, is it's a program that I participated in with my students before coming to moving into astronomy, transitioning into this different career field. I spent quite a few years as a high school teacher, high school Spanish teacher. And while I was working on my another degree in astronomy, which I started here, that was the reason I moved to Hawaii, I had the opportunity to get connected with Mauna Kea Scholars. And it has been so amazing to see what young people are capable of. Yes, we're sharing. Okay, so I'm going to actually go here. You can explore a little bit. When you go down a little bit further, you can see some videos, and there in the blue is Mary Beth Lachek. Now, she's from Canada France Hawaii Telescope, and she has led this program. Now, for me as a teacher and a student at the same time, what I learned a lot with my students. So one of the first things we did was to teach our students how to read scientific papers, because it can be really dense and difficult to approach, especially with all of the jargon that they may not be aware of. So I was learning along with them, as part of that journey, how to interpret and pull out and extrapolate the most necessary data. Then this program pairs us, it pairs the students and the teacher as well with a postdoc or a grad student or actual working astronomer to help guide us through learning how to write an abstract for a proposal. And while we're doing that, we expose the students to all kinds of cosmological mysteries and excitement, from black holes, exoplanets, to studying different bodies in the asteroid belt, comets as well too. Where can we find water? All of these different kinds of thoughts and ideas that the observatories here on Mauna Kea can give us insights to. And once our students, once we went through that process, which is about a semester, then the students worked in groups to submit an actual proposal. And again, part of the support that Mauna Kea Scholars provides to the students is not only instruction on how to do it, but it empowers them in realizing that they have the skills already to build on, to work with this data and to learn to write an abstract and a proposal, that it's not outside of their ability to do once they have, some instruction, some understanding and support. And so out of, I think I had maybe 5 groups of students who submitted proposals. 3 of my groups the first year doing Mauna Kea Scholars actually received telescope time. And if you scroll down, you click on students, you can click on students, and there is a video there. You can click on students. I realized this is actually me and where I was working at earlier. This is a great video with she was a junior at the time, Amber Nakata. And she went on to do Mauna Kea Scholars several times and was going to study astronomy, cosmology in general when she got to university. And this is a great video with her. But her excitement really did is an example to actually of how excited everyone was. And that's in the midst of, you know, lots of changes going on in the mountain. The students were still really excited to get their hands on data and to really understand what the life of an astronomer was. And this program, Mauna Kea Scholars, really has allowed that exposure. And as Brian mentioned earlier, or maybe this was yesterday, but we have every decade, we have a decadal that comes out for planetary sciences, for astrophysics as well too, and other fields. And this particular year, last year, was the first time they actually had a state of the profession portion of the decadal. And the decadal really helps set the targets for where we're going to in the next decade for the US. What should those main science targets and goals be? But the state of the profession was new in this decadal, and because the lack of representation in the field, lack of representation of society as a whole in the field is something that we really want to address. And programs like SIP and Mauna Kea Scholars, and of course Shadow the Scientist, is something that will help to, I hope and believe, change that tide for the better.
Jamaica, I'm noticing that Kapolei High School, which is mentioned just below the video, is where Arya goes to school.
Oh, really? Are you,
Yeah.
you're in Kapolei? Okay, I know Kapolei. I lived on Oahu for several years when I was teaching here at Nanakuli High School under Darren Pilialoha here with the lay on. And to the left, you can actually see at the time, that's Doug Simons, who was at the time the director of the Canada-France Wide Telescope, who is now the director of the UH Institute for Astronomy. You know, it was fantastic for all of our students to actually engage with the astronomers, with the postdocs, with the grad students, and with each other. Arya, have you done any Mauna Kea Scholars work there at Kapolei?
Arya had to hang up, I think. I don't see her on the call anymore.
Okay.
She did sign off. She said, you know, she has an early morning thing tomorrow.
Okay.
I don't see her on the call anymore, but yeah.
All right, Roger, thank you for sharing that. I did not realize Arya was on Oahu. But yeah, so the science internship program, Mauna Kea Scholars, Shadow the Scientist, these types of programs are amazing. It's an amazing vehicle for bringing exposure to these underrepresented groups and to people actually who are in rural areas, who are far away from being able to get that exposure and contact, even if it was available. So these are vital for the continuation, not only of this field, but to gain more perspectives, more voices, which of course will help us have a better understanding of the universe. All right, so yeah, definitely check that out. And can we do a quick check-in, Zach, with our observation team? Oh, Zach, your face tells me the weather is maybe not improving.
It has cleared.
Oh,
but the humidity is still like 97%. So
100%.
yeah, what it is 100. Yeah. So it has cleared up, but yeah, this is one of those situations. But you can also see on the north cam that something else is developing a little bit lower and starting to creep back up.
See that? Oh,
so,
but also in that north camera, right here, for those who have not been to Hawaii, I believe that is Maui, right? That ridge in the back. Yes, Haleakala. Yes. All right, Charlie. It is quite amazing when you're on the north part of the island, or even on the Kona side, to be able to look out and see Maui rising in the distance. And of course, you know, astronomy was done on Haleakala early on, and then they realized that this could be also a good place to do some astronomy from here on Mauna Kea. So it is quite amazing to see that it looks beautiful outside. And you'd imagine we could just open, but these are one of those subtle details that we need to be aware of. And in fact, I think it was Marufa was saying earlier about her, cleaning her mirror and the difficulties that brings. This is the kind of thing that anyone doing astronomy, whether it's a 70 millimeter or 10 meter telescope, you are subject to the elements, to the weather, all of it, regardless of the size. And that's one thing that brings us all together. And I feel like that really helps us to see that, if you're interested in astronomy, we're all astronomers. We're all getting understanding of the universe and of the things that we need to deal with in order to gaze out clearly and get an understanding of the wonders around us. Oh, Zach, it's 8:47.
It is 8:47.
Oh my goodness, we're heading up to hour 3, which is pretty awesome. So maybe we can talk a little bit before we wrap up in maybe 13 minutes, Zach. Does that sound good to you?
Yeah.
Before we do that, is there a way for us to look at maybe some older images from previous programs, since it looks like we're maybe not going to be able to open tonight, then we can maybe see what an image may look like if we were observing sometime.
Yeah, I don't know whether Brian has any up or anything like that. If not, I can go search.
No, I don't have one right now, Zach. I could bring something up, but yeah, if you maybe want to show people the archive, and maybe you can show even the so I do have actually the observing tool up in your 5th screen, and I'm showing just like a kind of basic observation that I've made up, and so maybe you can show that, and then we could show the archive.
Yeah, let's do that. All right, and we're sharing. So yeah, do you want to take the reins, or do you want me to take the reins?
If you don't mind explaining it, I can try to look up something on the archive, or vice versa, however you like.
Well, seeing as I can't really, well, okay, unless you want me to turn interactive mode on and take over your screen.
I don't want that. So how about I explain what's going on here? So yes, this is our observing tool. So this is the main tool that we use for basically, well, a lot of parts of the constructing of the observation and then taking the observation on a given night. So this is my workspace here. So this is where I can put test observations to kind of test out different modes. If a science team sends me something and that they're interested in a particular type of mode, a particular type of observation, I may bring that observation into this software workspace and play around with it. So there's a lot of stuff going on here. But the basic idea is that each one of these things in this list are a different observation. And what that means is that it's we would slew to that, so move the telescope to that target. So in this case, I have a random target called Subaru 2. And so we would move the telescope to there. If we had selected that observation based on scientific merit and based on the conditions, in this particular case, I would, set observing conditions. This one's very liberal. And so I could change the sky background to be the darkest. So definitely not right now, since we're nearing a full moon, I think. Yeah.
Yes. Yeah, full moon on Sunday, I believe.
Okay. Yeah, so we would be in bright conditions right now. So this observation could be taken any cloud cover, so meaning we could have pretty decent clouds and still be okay. Any image quality, any water vapor. So this one, if this were the actual conditions, we could if we could open up, we could take this observation. And so this observation consists of a Genius setup. So this is, we take the telescope light that goes off the primary and hits the secondary and goes into our instrument structure. If Genius were on the telescope tonight, which it's not, it's getting ready to be upgraded for the shutdown, then we would pipe the light there.
So basically reflect the light there into G-nears. And this is taking a cross dispersed observation. So this is a spectroscopic observation in the near infrared. So past about 1,000 nanometers. And the cross dispersed part of this observation means that we use diffraction grating and a prism. So both of these disperse light into its constituent parts. So you take a white light, but this is of course in the near infrared where we can't see, and you disperse it both in the X direction and in the Y direction. And so you get basically the whole entire near infrared portion of the spectrum that we can see from the ground, which runs from about 1 micron or 1,000 nanometers to 2.25-ish microns. So that is all in one observation. And then we take a sequence, which in this case, actually, so I was just messing around with this. So this is just a calibration sequence. I'm taking arc line observations. So this is an elemental lamp that we turn on. And Zach mentioned about this GCal part of our instrument support structure. So we take this science fold mirror, which is our tertiary mirror, and we reflect light in between the GCal chamber that has different elemental lamps and reflect that into G-nears for on the telescope. And then we get a calibration. So this could be to understand which wavelength. So we have our image on our detector, which maybe Zach will show some examples of that in a second. So our image on our detector, and we have X and Y locations, and we have intensity. And we want to map that into a series of numbers which indicate intensity at a given wavelength value, because that's what's really interesting to us. And so in order to do that, we need a baseline standard to determine where on that X and Y, so which X and Y location corresponds to which wavelength of light. And so this is why we would take a calibration observation like this. So in fact, this one we could take while the telescope is closed, because we're not actually using anything from the telescope itself. We're just using some light being reflected from our GCal calibrator lamp in our instrument support structure to another instrument in our instrument support structure. So we don't need the shutter open. We can just use this as an internal reflection. But I actually have a target here on sky, so this is a calibration without an actual observation on sky. But of course, I could add the observation on sky, so we interact with this all the time. So a science team will propose for a certain object, and then we work with the science team through this observing tool to be able to get everything ready. And so, supposing we were actually doing this, this picture here shows. This picture here shows what that observation might look like. So we have a static screen in the back. So this is a digital sky survey. This is probably high band. So this is probably about 800 nanometers, the observation. And it's showing what this portion of the sky will probably look like. This is taken a long time ago and with the smaller telescope, so it's going to look much brighter with our observations. And so Zach mentioned something about wavefront sensors earlier. So this is our probe arm of our primary wavefront sensor, the second primary wavefront sensor. We have two of them. And this is our slit for the G-nears observation. So it's a slit that pipes the light only from the object that we're interested in. And so this yellow region actually shows, I didn't make this observation very well, because we're looking down, we're basically looking up at it. So we're looking up at the sky like this. The wavefront sensor, the kind of transparent yellow region, is blocking our view of the target. So if you can see my mouse here.
Yes.
Yeah. So you can see the yellow region is very, very close to the target, which is this little thing right here. So so this little box right here was actually our target. And you can't see it in this image because it's probably much, much fainter than this image goes to. Yeah, so this actual mechanical arm would be coming very close to blocking off
our target. So we would actually want to pick out a different star, and this particular observation, we don't have a different star, and so so this observation would be very, very difficult. But if we were, working on trying to make this better, we might, play around with moving the where the instrument is pointing a little bit, and that would allow for different stars to be picked up. So I could move this arm like this, so that it's not blocking the light. So that whole process is our observing tool, and I actually would you be using that right now. If we were open, I would be using this Q button, which is up here. And so let's say, we decided that we wanted to go to this observation tonight, then I would queue it up. So using that as a verb, and then we would actually execute that observation, which means we would start configuring the instrument. We would start configuring the telescope, and then we would shine the light into the Genius instrument if it were on tonight, and actually take the observation. So this tool is used both to set up observations and to take the observations. And then after the observations are taken, then I would pass to you, Zach, for showing us what those might look like.
Yeah, so I have one here, although if you could send me the GMOS one, that would be great. Because I can't remember what RA and deck you were looking at.
Oh yeah, I can't either.
Ah, great. All right. Well, so I can at least show more Speckle if you can look at if you can quick find that Cal program.
I'll take a look. Yeah.
Okay. So I will show off the Gemini archive first. So this is the Gemini archive, and so the great thing about Gemini is it is a public observatory. So all the data is made available on the Gemini archive after it's taken. Now there are some restrictions. Gemini has a proprietary period where for I believe it's either 6 or 12 months. The person who proposed for that program has strict access to the data, in that only they can download the data. After those 6 months or after that proprietary period is over, then the data is free game to anybody and you can go look it up. But I happened to get a program accepted last year, and so I went and looked up one of my programs and I grabbed the data. So this is actual Gemini data taken with Zorro down in the south. And so because I'm a Speckle imager person, this is a Speckle data frame. And so what we get is a data cube, as I said before. And so each cube is 1,000. And as I move this back in time, you can see the speckles kind of hopping around again.
Oh, yeah.
So this is kind of the real-time observation of what happens in one Speckle data cube again. But so because of this proprietary period, we can't really show a lot of the science that goes on here. But what we can do is kind of show off some of the calibration images that we normally take. So Brian, do you happen to have an RA in deck for me? Or I can just
put it in the chat. So
there we go. Okay, so for this one, for example, you would put in here 16, 35, 35. Oh, well, that would be if the numlock was on, then it would. And then the declination is 09, 48, 16. And RA and declination are the coordinate system we use to tell where an object is in the night sky. And so if we search here, ta-da, there's this whole bunch of stuff here from this field that this program looked at as a calibration. And so one of the great things that is hopefully going to be happening in the next couple of years and will hopefully in the next 5 years or so is we will have this ability to basically look at the Gemini archive and grab the data and look and get like a first look at the data. And so I believe it's this one. Yeah, this one gives you a preview of what the data is supposed to look like. And so you can see here there are a couple bright stars in there, and you can also see some of the characteristics of our GMOS detector. You know, it has this this rectangular shape, and then it also has these dividers dividing the CCD, the device that gathers all the light that we take in with the telescope. You can see that it is divided into 4 areas on this image. And so what this program would do is use these stars. These are all stars that have known brightnesses. And so what the program that took this data would do is they would take these stars, measure, okay, what's their flux they're given there. That flux gives you what the flux and the magnitude of the star should be. And so if you have that information from this image, you can then go to your science image and get like absolute photometry on your data. Otherwise, it's what we call relative photometry, which is more it's not absolutely calibrated. It is a relative thing.
I have a question. Zach.
Mhm.
I have a question. Can you explain flux?
Yeah, so flux is basically a measure of how much light is coming and hitting our detector. So normally you observe for a certain amount of time and you get a certain number of photons from the star. And flux is then our measure of what that is.
So it's not exactly, so say the star is putting out 20 photons, but we get all 20 of those photons?
No, so the star is sending off that. So then, flux is, whatever hits us at our detector. So if it's pushing out 20 photons total, these photons are spread all over as it emits this light, and then we get a certain fraction of that. And so normally, flux is this parameter that has units corresponding to that. It has units of basically whatever your surface area of your detector is. And so at the end of the day, you can get a flux that gives you, photons per second. And that's whatever's hitting your detector, or you could have different, or you could go back and actually it's more like a flux density rather than an actual flux. But at the end of the day, what you're looking for is to get a flux from your star, nominally in ergs or ergs, whatever.
Ergs per centimeter square per
Yep.
second. Because it's not the centimeter square of the detector, but of the telescope, because the telescope's the one that's focusing the light.
Sorry, I got that confused. So once you take out the how much light is collecting from the telescope, then you get ergs per second. And then that allows you to calculate, it gives you the flux, then you can get a magnitude from that flux. And depending on whether or not you have this calibration image, then you either have a relative magnitude or you have an absolute, or you have relative photometry or an absolute photometry.
Okay. And so when we're looking here and we have those 3 lines, is that a mechanically built in because of the detector? Or
Yes.
Is that okay?
Yeah. It's a detector characteristic.
It's a detector characteristic, so not like an emission line. Or
No.
Yeah, I know. Yeah, it doesn't look like an emission or an absorption line. I wasn't sure. Okay, and so once you have this image, then you do what with it?
So you use it as part of your data reduction pipeline. So as you go through the science, you take the data, and then when you first take the data, there's a lot of, I wouldn't say them problems, but a lot of things that need to be corrected in the data.
Oh.
So you need to correct for the fact that when you read in the detector, when you read out a detector, so when you download the data from the detector, there's some noise associated with that. And so we have to take that out. there's some across this field that we're looking at, there are some telescope aberrations that can be taken out through what we call flat fielding, which is we take an image of in a Gemini's case, we use twilight flats. But in flat fielding, you take an image of basically this white sheet on a wall, and that allows you to map out where the telescope, where kind of there's imperfections in the telescope. So let's say like there's a dust somewhere, a
Mhm.
dust particle somewhere, then you can like model, or that can be flat fielded out.
Flat fielded out.
In Gemini's case, we use twilight fields, which are basically blank twilight flats, which are blank areas in the sky where there's not a lot of stars. So that allows us to map out where everything's going on.
Ah,
And then there's a couple of other things, but those are the two main ones. There's also biases, which is just kind of the inherent noise in the detector that needs to be subtracted out. But so the data reduction pipeline is basically you taking all those into account and getting rid of all of those. And then at the end of the day, you have a science product that you can go and do science on.
so okay, that process from getting this kind of image to doing the reduction that takes out all of the noise and extra artifacts that you don't need, to having something that you can now work with. What's that general time frame?
It depends on, a lot of different things. So, for imaging, doing a single image, it could take like 15-30 minutes. I don't know. I haven't done this kind of data reduction in a while. For myself, when I do my speckle reduction, it takes days in order to do it.
I'll just jump in for a second.
Yeah.
So one of the things that we were going to have running tonight, and we will if we open up, is our quality assessment pipeline, and this is a Python-based quick reduction software. And I think let's see. Oh yeah, it's not running right now because we're not feeding it anything. But yeah, so we have this quality assessment pipeline here, which is based off of the reduction packages that are people that work on the software here at Gemini have developed. And so this can actually reduce very, very quickly a single image. So we can get an entire mosaic of images. Like, so last night, what was I taking? I was taking observations of Io, one of the moons of Jupiter, and I was taking observations of an asteroid that's very bright. It's passing fairly nearby to Earth. And we were taking images at different locations. So we were basically moving the telescope around, always with Io or the asteroid in the field of view, but to average out some of those detector issues that you were talking about, Zach. And so this mosaic of images, it would process it, and I would be able to see the actual process frame within, I don't know, a minute, 2 minutes of me taking the observation. So this as telescopes are coming online that have tons and tons and tons of data, you want something that efficiently processes those data and does it well and does it quickly. And Gemini, we're kind of a pinpoint observatory, but there's plenty of observatories that are looking at the entire sky that are coming up soon. And so we're really tied to how quickly, efficiently, and well done our data reduction processes can be. And so there's plenty of people at Gemini that are working on that. And yeah, the ultimate goal is to have this available for people on the archive as well, so that they can take science-ready data and do their own science with it.
Yeah, and so for data on the archive, right now it is the raw data. It's not corrected or anything like that. So whoever downloads the data, they would have to go in and they would have to correct it. But as Brian said, the ultimate goal is you want to at least have the raw data somewhere, but you want to also have a quick look science ready data product. So that's something that we are striving for in the future.
That, that is ready-made for someone like me in school, or anyone, high school students or anyone, to be able to go in and do some research themselves from the archive data, which is pretty amazing. And we talked about this before at some of our dry run sessions, but my Python skills are increasing, yes, but not quite there to be able to run the data reduction program on my own. But I believe there's a tutorial on the archive. Actually, there's some instructions on how to do that. And I looked through it the other day, but definitely check that out if this is something you are interested in doing. And now we have a question here, and thank you for the question. Would the data on the link shown already have been corrected or reduced, or would it be raw? Yes, and so I believe that's exactly what Zach spoke to, that it would be raw. And then once in the next few years, when things progress and we have the actual data reduced images for you to get, that will be pretty amazing.
There's many observatories, like for example Hubble, they offer nearly science ready data on their archive, and so you can actually take that off and you can do like rudimentary science with those observations. And a lot of observatories are moving towards this model. It's very, very important for us at Gemini. It's very important for us that people are able to reduce their data, because if you can't reduce your data or do it well, or if there's too much of a barrier, it's too complicated, then it's much harder to do science with the observations that are being taken. So this is all part of the observatory, the life of an observatory. We want to make the observations, we work very hard to make those observations as good as possible, to get the most amount of scientific leverage out of the time that we have. And then we want to make on the back end, we want to make science users, we want to support our science users, which is what David is hired to do, and support our users so that they can produce the data well, and that they can share their results with everybody. And so that in turn, they're not going to look at everything. There's plenty of other maybe they're focused on a particular source, a particular asteroid in the field of view, a particular high redshift galaxy, but there's tons of other stuff that's going on in those images of those observations, that once that is disseminated to people, that it's much easier for people to actually take that and run with it, and do their own science.
Yes, absolutely. I've definitely been interested in being able to do that, but I haven't so far. And in fact, it was just some months ago that I learned that Gemini even had an archive. So I'm going to dive in and try to check that out. Raja, yes, I see your hand.
I have 3 random remarks related to things that we've been talking about. One is,
yes,
I know we astronomers talk about reduction of data, and I just wanted to clarify for the non-astronomers in the Zoom call, of which there are not many at this point, but when we talk about reduction, the way I like to think of it is we are trying to separate the astrophysics from the atmosphere, from the instrument. So when we get something, when we collect information, it's a combination of those 3 things. There's some instrumental signature, there's some typically Earth's atmospheric signature, either an absorption or emission, or both, and there's the astrophysics of the object. Sometimes there are other things, there's the astrophysics of things between us and the object. But when we're talking about data reduction, it's typically removing the effects of the atmosphere, Earth's atmosphere, that is, and the instrument. That's one random remark. I have 2 more. Those are shorter. I know you mentioned, Zach, I think you mentioned flux. We were talking about flux, and we were talking about flux density briefly. Is that right?
Yeah.
And the only change, so you're absolutely right that when you want to get rid of the centimeter squared, it's not just correcting for the area of the telescope, you have to correct for the distance to the object.
Right.
And once you do that, you turn it from an apparent to an absolute magnitude. That's one thing. And second, for the density, for a flux density, where instead of ergs per centimeter squared per second, you have to add per hertz or per angstrom, because it's per unit of, that's relevant to a spectrum. It's for a tiny slice of the spectrum, and that's sometimes that can also be written in Jansky. Radio astronomers use Jansky, but it's essentially the same unit. Per hertz translates to Jansky. And then one final silly remark, and that is, I'm fascinated by speckles. I haven't done speckle imaging, but I've been fascinated by it for a while, from the time Andrea was doing this in her study of the galactic center black hole.
Andrea Guess.
Andrea Guess, right? So I find a useful way to think about a speckle, a single speckle image, is because of the effects of the Earth's atmosphere, the wavefront from a distant star isn't a plane wave. It would normally be a plane wave, if there were no distortion. It would be a perfectly plane wave, would strike our Keck mirror, it would form a diffraction limited, or Gemini mirror, form a diffraction limited image. Now, because of the effects of the Earth's atmosphere, this wavefront has become sort of this crinkled surface. And you can think of this crinkled surface as a series of planes, tiny planes, and each tiny plane is at a different tilt, and each one creates its image of the star. That's why each image is faint, but each image is also in a different location because of the tilts of the, in other words, you can think of this crinkled wavefront as a series of small planes. And small, therefore, it's not using the full area of the Keck telescope. That's why a faint image of the star. But because these planes have different tilts, they form images in different sections of the detector. That's what gives you the speckle. I don't know if that makes any sense. Sorry for this long and silly remark.
No worries.
Definitely not at all silly remarks.
People are thinking speckle, that was so 5 hours ago or 2 hours ago.
But no, but I appreciate the additional details, because that you connected us to Andrea Guess, who is a graduate of Hilo High School, by the way. I'm going
No
to
kidding. No kidding. I didn't know that.
Yes, she sure is a graduate of Hilo High School. And of course, is a Keck astronomer. I'm going to drop in the chat when I can pull up the chat. There we are.
I had no idea she was from Hilo. I know she went to undergraduate at Caltech.
Yes.
And she was no, sorry, she was a grad student at Caltech. Where was she an undergraduate? I don't know.
Maybe this link that I just dropped in the chat will tell
I
us.
probably have that, yeah. She got the Nobel Prize recently in physics. Yeah,
yes.
I'm looking at.
Yeah, she sure did. Did they talk about her? Oh, they didn't put this here. Yes, I've had a number of opportunities to meet her when she her and her grad students were here doing some of their work studying the galactic center. I think maybe she was one of the first famous astronomers that I saw on the mountain, and it was thrilling. And then especially finding out later that she's a graduate right here of Hilo High School, and has done amazing things, and is giving back to the community in so many fantastic ways. Yeah, so that's in the chat. Any more comments, Roger? Because those were pretty amazing insights, I have to say.
I just remember a very early conversation with Andrea about Speckle when we were both new faculty. We're exact contemporaries. We started our faculty positions at exactly the same time. But I remember we were MIT undergrad.
MIT. Okay, nice, Rob.
So we were both, I think in those days we were observing from it might have been the summit even. I remember having this conversation with Andrea about Speckle a long time ago.
I didn't realize you all were contemporaries. That's wow. Walking
not in fame, only in chronology, just to be clear.
Oh, Raja, no, I am sure you've had so much, an amazing impact on me. I've known you for a month. So I am sure that your reach has very wide breadth for sure. And I have to say, as I said at the very beginning of the session, Shadow the Scientist for me And I'm grateful to be able to participate with my amazing colleagues as they guide us through the shadowing process, shadowing our scientists in the control room with, Zach as our guide this evening. But as a student, Raja, you have impacted me in so many ways. And I think I've shared just a little bit, but my interest in research, understanding what's actually going on, having a safe place to ask questions and not feeling uncomfortable to ask those questions. That's just a few things that you've done for me as I become, part of the Shadow of the Scientist group, watching the sessions and then now participating. So thank you for that.
That's very kind of you to say, Jamaica. I mean, I'm so glad our paths have crossed, and I thank Brian for bringing this connection to me, bringing you to me. And of course, I'm grateful for my connection to Brian, which also goes back a long way to his student days. So all good.
I love the connections. I love the connections. Okay. Oh, we went a little bit slightly over, which is all right. It's 9:21. Okay, so let's go back to the control room really quickly, and for real, we're gonna wrap up for real this time, Zach. I know I said that 40 minutes ago, but for real. We can pop in now. Brian, how's it going? I see you pacing, so I'm thinking what, still a lot of humidity.
I'm pacing because it's gotten a lot chillier here in the control room. So that's the main update here, Jamaica. The weather in the control room has gotten chillier.
I think it's cold over there.
No, actually we saw, I don't know if y'all saw this in the cloud cams, but Keck 2 actually just opened.
Oh, let's take a look at that cloud cam, Zach.
You have to watch the animation of them opening, and I think you might even get to see a mirror.
No, they've got a dome light on.
Dome light, yeah, okay.
Oh, nice.
Yeah, so they just opened. So that's good news, not for tonight's Shadow of the Scientist session, but maybe for later tonight we can actually get some observations in. Which would be awesome considering what we saw earlier in the cloud cams and what we were getting on our monitors earlier. But yeah, that's what's going on here. So we're gonna stay here, wait it out. Though that might be a while, so we don't want to keep everybody on the call until then.
Absolutely, absolutely. You're right about that, Brian. But really quickly, now, so Gemini is on the eastern ridge facing out west towards Keck. And Charlie and Zach spoke earlier on the difference in humidity just right across the ridge, because what's the humidity right here where we are now, Brian? Because clearly it must be less for Keck over there.
Yeah, the difference is not so much actually between the two. So I'm the registers on the Mauna Kea Weather Center are saying 87 for us, and that looks in the neighborhood, somewhere between 87 and 92, and Keck is at 81. But they actually have different metrics, and they can open. They can open. They're maybe a little bit more adaptable than us in some ways, in terms of how fast they can open and close. So they have different metrics for opening, and so so each observatory decides that for themselves, and they've determined that it's safe for their telescope to open up right now. So they're taking their first observations of the night, and usually we're not far behind them. So hopefully that bodes well for us.
I hope it does too. So Zach, as we wrap up here in the last few minutes, let's say we were going to stick with the observing team this evening. Once we open the dome, what could we expect once we finish the shutdown and we have our next session? What can we expect to be sharing with those who join our next Shadow of the Scientist session and we're actually on Sky?
Well, hopefully some data. But I mean, we'd be able to see more of what Brian would be doing on his side, showing off, checking the data as it comes in, making sure that the data actually has science in it instead of just being pictures of empty sky or something like that. And actually seeing this observation getting queued up, as we were talking about with the ISD, seeing the different bits and pieces of the instruments moving around, and seeing some data being taken in the queue being observed.
Data, yes. So and in fact, I'm glad you said that, the looking at the queued programs, because I realized that I don't think we spoke about the roles that we have in the control room. And well, actually just for the observing team. So we have the operator, we have an observer, and we typically sometimes have a laser support staff as well too.
Yep.
And so could you really quickly tell us what the observer does? Because I believe that's Brian's role this evening, correct? And is Charlie our operator?
Charlie and Pablo are operators.
Charlie and Pablo are our operator. And so we don't have a laser support staff.
Nope.
This evening, no. Okay. And so as the operator, what is their main role?
So their main role is to point the telescope to the targets that the observer says, hey, we're going to go observe these. They set up all the necessary requirements for the telescope, the guiding, the slews to it. They make sure that when we stop overzealous observers from observing during the night. Charlie, you want to chime in on anything, or?
Yeah, sure. So the operator is primarily responsible for the health of the telescope and detectors, and for getting the telescope to where it should be pointing for the science observations and setting up guidance. So we have that role of slewing the telescope, moving the telescope, and setting up guidance. It probably takes up most of our active time. The telescope has computers which guide it to allow it to track objects on the sky, but we take many small images with specialized cameras called guiders, or wavefront sensors, that allow us to both correct the pointing of the telescope to make sure that we stay looking in exactly the right spot over the length of the observation, and allow the telescope to correct for at least some of the atmospheric conditions. And so we set up on a guide star at the beginning of nearly every observation, and that's actually a lot of our intense duty as we're working here. But we also keep an eye on the health and welfare of all of this system. So there's many different components of the telescope itself and of the detectors that we have to make sure stay healthy for science to take place.
Yeah, thank you, Charlie, for giving us a little bit of insights and details on the operator's role. So now the observer's role is to then what?
So the observer is, I'll step in here because as I serve both, I can do both tasks. The observer is going to direct the flow of the actual observations, the actual science of the evening. Earlier in the day, a Q coordinator has gone through and made up a list of several, maybe 3 to 7 different variations on what the sequence of observations might be for the night. Each of those variations is for a different combination of weather conditions. If the seeing is good, if the cloud cover is good, or if the cloud cover is a little bit worse, if the seeing is still okay, a whole bunch of different possible permutations. And the observer is going to watch over those different sequences, those cues, and look at the current conditions, both all of the data that Brian has discussed earlier, also the cloud cameras that we've taken quite a bit of look at tonight, and make the best call about what observation should be, what is the best observation that we could do, what is the best way we can use the telescope time, given the weather conditions, given the seeing conditions. In a way, I like to think of the job, as someone who used to be very interested in history of United States railroads, I always like to use the analogy that the operator is sort of the engineer taking care of the equipment and actually doing the driving. The observer is a conductor telling the engineer where to go and when to go. We both have our different roles and that are very well defined, but work together as a team to get the science done.
Seamless synergy, it seems like. And I didn't realize that
As
you,
long as the observer listens to the operator, it's seamless.
as it should be, as it should be.
And the observers and the operators listen to the day crew and the
Absolutely.
coordinator and the head of science operations. And so, yeah, I mean, just to speak to that, like there's plenty of roles that aren't being represented here. And so as Charlie mentioned, the Q coordinator, which is somebody that has to come up with plans for all different possible variations of what might happen that night in the sky and on the ground, you know, an immense amount of work. And we're, as observers, we can call them at any time of the night if we have an issue with some of the observations. So, you know, as I mentioned earlier in the session, we don't necessarily know the science intimately for every single program that we're observing. And so talking through this process with another person that has familiarized themselves with the observations that are being taken that night potentially is really, really helpful. So they're, you know, even you know, a conductor on top of the conductor,
Right.
But you know, we all work in concert to make sure that, you know, we're getting the best observations for that particular time. And of course, our wonderful day crew, who are going to be performing all this work that we've talked about earlier for the shutdown, you know, they're the actual ones that go up and, you know, interact with the telescope hardware. And so we better be listening to them if they're saying, oh, you know, something doesn't seem right with, you know, one of our instruments or something. So everybody works together as a team. We all have different eyes, different perspectives. We come from different backgrounds. And so, you know, and we speak different languages, both, you know, actual different languages, but, you know, we are steeped in different, you know, history and we come from different perspectives. That could be cultural, that could be, you know, our training. And so that's, I think, you know, what makes observatory life so amazing is that we have all these different people that come from all these different backgrounds. We're a multinational observatory with everybody using it. And we all have the same mission to do this thing. And
yeah, I think that diversity is really important. I mean, for example, Brian here is a visible infrared astronomer, and my training is as a radio astronomer. We get along just fine. So that's proof that pretty much more or less. So they're proof that almost anything is possible.
I didn't realize that your background was radio astronomy, Charlie.
Radio and submillimeter.
Oh, radio and.
So I have, you know, as an astronomer, I have used one of our neighbors up on the summit, JCMT, James Clerk Maxwell Telescope for Science. Never used this because my science can't do this. Can't benefit from a place like Gemini.
But we're using their observations now, right?
We're using weather data that they collect.
Yeah, so I mean, just to speak of, you know, not only just for Gemini Observatory, but you know, there's a spirit of collaboration up on the Mana too between the observatories, sharing data, sharing. You know, we have a weather monitor here from CFHT. We have JCMT weather monitoring for water vapor in the atmosphere. We actually have an instrument which we didn't talk about tonight, but which will probably come up in future Shadow the Scientist sessions called Graces, which actually is housed at CFHT, and we use our telescope for the observations. So yeah, there's a spirit of cooperation in trying to, you know, this is a wonderful astronomical site and trying to use it to best of its abilities.
And again, to add to that, the operators up on the summit actually have a Slack channel, a communication channel that we are constantly exchanging information about weather conditions and seeing conditions. Someone at, you know, some of the telescopes are actually still operated at the summit. And so those people may go out with a flashlight to look and see if they can see particulate matter in the air or snowflakes. And they will let everyone else know. So we all, there is undoubtedly at some levels of the observatory relationship competition, but really amongst the staff, amongst the astronomers, I think it's all, certainly among the operations staff, it's all cooperative because we are all, we're all in it together basically. But that's a really neat sensation to be sort of part of that larger network.
Absolutely.
Of course, you have a lot of countries represented at the summit as well. So this is not just United States observatories. So it's very much multinational, very diverse.
Thank you for sharing that, Charlie.
Yes, thank you, Charlie. Thank you so much. Gil, this has been such a fantastic adventure. Zach, you have been an amazing guide on our first shadowing session. Shadowing the scientists here in the control room at Gemini here, of course. Oh, sorry. I thought you were saying something to me. But yeah, this has been an amazing journey. You've been a fabulous guide. And so before we leave, Raja, we do have upcoming Shadow the Scientist sessions. Would you like to, not at Gemini, of course, because we will be starting the shutdown on Monday, and not tomorrow, but on Monday in a few days. So we'll be back with a shadow session most definitely after that. But other shadow sessions are already scheduled. Raja, would you like to speak to that?
Sure. I think we have a string of them. I think Brian's hosting the next one exactly a week from tonight. So next Friday, the 14th, I think is Brian and Roy, and this is on Keck 1 and Mossfire. I think I'm on shortly after that from Keck 2 and Demos. And then I think I'll have to look at the exact schedule, but I believe we have a string of nights coming up.
Yes.
In October, and then more in November, more in December. We haven't posted anything in the new year yet because we don't know yet. Okay, so the nights that are coming up are actually early hours of October 15th. So not next Friday, but really early hours of next Saturday. Then we have, that's October, like night of the 14th, wee hours of the 15th. I'm on the 18th. I'm on again on the 22nd. My colleague is on the 26th and 27th of October. I'm on again on the 28th. Then we have Lake on the 31st, Halloween. We have several nights in November again. So all on our website, all on the Shadow website. So this is terrific. And I just wanted to point out, I did a little bit of detective work. From what I can see, row C is at capital A High School.
Oh, okay.
I believe we have a couple of other Hawaii folks on the call. I think Tom is in Hawaii, if I'm not mistaken, and Richard as well. No, Richard is in California. Richard and Rob are in California, if I remember correctly.
Mm-hmm. And Tom is just a few hours from Mauna Kea.
That's right. And Vonnie is in Memphis.
Yes.
If I remember correctly.
Yes, absolutely. That is right. And we had, although this student only joined for just a moment, but we had Aaron from Kamehameha Schools here.
Yes.
He was here for just a moment. He joined the session that Brian and I were with you and Stefan and Antara at Keck a few weeks ago, but he joined this session at the very beginning for like 3 minutes to say thank you. One of our other astronomers and Brian as well met with Aaron earlier this week, and he came to visit the control room, and he's a senior, and Julia Schwartzer is supporting him with his senior legacy project. And so he popped into our session earlier to say that he really appreciated the tour. He's so excited to be working with Julia, and he got to meet with Brian as well too. And he's looking forward to joining upcoming sessions, Raja. So that is another Hawaii person.
That is wonderful. Look, and you guys are so true to the name of the program. It's really about scientists rather than science. It's really about people connections, and so much of that happened in today's session. So thank you for that.
Thank you for that awesome feedback, Roger. We appreciate it. All right, so it's 9:40, Zach. We're maybe an hour and 40 minutes over what we planned, but I am so excited about how well everything went. And I'm going to echo some of the comments in the chat that I learned so much, not only just from this session, but working with you and Raja and Brian has really been not only a confidence booster, but it is allowing me to see myself as a scientist as I'm working on this degree. So thank you, Zach. Thank you, Brian. Thank you, Raja. And I would say thank you all for joining us. And I'd like to leave the final words with Zach and then to the control room.
All right. Yeah. I just want to echo everything you say and add that, thank you for everything that you've done for this. You've really helped make this into what it is right now. So at least for Gemini, thank you, and Brian and Raja again for all of that. And yeah, we'll see everybody after the break. I have no idea who's going to be doing that next one. So, we'll see what's going on over in the control room. Brian, Charlie, Pablo.
We'll leave the last words with you in the control room, Brian, Charlie, Pablo.
I'd like to echo everything that you just said, Jamika. I mean, so I think one of the things that's really awesome for me in these sessions is how much I learn as well. I mean, the interactions between everybody here, again, we all have different backgrounds and coming from different places. And, like some of the stuff that you told us about, Charlie, was amazing. Like the shows that you guys shared. I don't know, I don't know that much about Speckle imaging. And just seeing, Zach, you walk us through that process, and
Probably just kind of spotty on it.
kind of spotty, yeah, thanks, Charlie. It was great, and I have some limited knowledge of the field that I'm really interested in astrophysics, but it's been wonderful. All the questions from the participants, and of course, all the engagement from Raja, Jamika, Zach. Everybody that made this an amazing session. So yeah, we will be shutting down in 3 days for Gemini North, but as Jamika and Raja mentioned, there's plenty of upcoming sessions, including the one that I'm running starting at 12:30 at night, Hawaii Standard Time, in about 1 week. So lots of wonderful sessions, and then of course we'll be back Gemini North at some point. You want to share anything?
It's always a lot of fun to talk about something that you're passionate about. So it's been a blast.
Yes, we could definitely hear that passion for sure. It's so exciting, and for me, this has been an amazing journey, and I'm looking forward to the next sessions, and not just the next Gemini session, but the next Shadow the Scientist sessions. I've joined multiple sessions, to prepare for bringing online the Gemini sessions, but just as a student to be able to join those sessions and ask questions in a safe space, not feeling any kind of pressure to engage or to have to be a certain way is really quite approachable, and I'm super grateful for it. So thank you all so much. And thank you for everyone in the control room for allowing us to follow you. And we look forward to catching up with you after the shutdown. All right. And so from the remote observing room here at the Hilo base facility in Hilo, Hawaii, we'd like to say mahalo for joining us. And we look forward to you being with us again next time. Aloha. And